Hello there and welcome to Life Beyond Seen, where curiosity drifts on calm waters and science takes its time. Tonight we set out together on a quiet voyage into a world long vanished, one that existed before forests, before bones, before anything with a face ever looked back at you. The seas of the Cambrian Period were the first great stage of animal life, and though they have been silent for more than 500 million years, their story is still written in the stones beneath our feet. It was a time when the world's oceans stirred with strange movement, when soft-bodied creatures learned the language of survival, and when hunting itself was invented. Before sharks, before whales, before anything with teeth, there were other rulers of the deep, hunters that looked nothing like anything alive today, yet laid the foundations for all that would follow. Maybe you're listening from somewhere quiet, perhaps late at night, with the soft hum of a world still awake in the background. Wherever you are, imagine for a moment that the walls around you melt away, and the air becomes cool and heavy with salt. Imagine sunlight trickling through shallow water, scattering into rippling beams that dance across a floor of silt. The continents have not yet taken their modern shapes. The air is thin, the land barren, and the ocean is where everything important is happening. If you find this journey soothing or simply a gentle way to learn something before you rest, a small gesture like a like or a subscription helps this little corner of calm reach others who might need the same quiet escape. Now take a slow breath, let your thoughts ease and drift with me downward into those ancient waters, because the story of life's first hunters begins not with teeth or claws, but with light. Before there were predators, there was stillness. The earliest oceans were filled with microscopic drifters, simple forms that fed on sunlight or absorbed nutrients directly from the water. They floated freely, unbothered by pursuit, existing in a slow chemical calm that had lasted for millions of years. Life was everywhere, but it was gentle. That calm, however, could not last. Every ecosystem, even one so young, tends toward complexity. When food becomes plentiful and competition grows, nature begins to experiment. In the murky shallows of the late Precambrian and early Cambrian, evolution began to accelerate. Cells that once lived alone began to cooperate. Bodies formed layers, muscles, mouths. Movement began. The world that had been still for eons started to stir. At first these movements were small, a ripple through soft mud, a faint twitch of cilia pushing against the current, an animal no larger than a grain of rice tracing a meandering path across the seafloor. These were the first steps toward motion, and with motion came the potential for something new: interaction. Once one organism could move faster than another, the idea of hunting was born, though of course there were no ideas then, only instincts encoded in the quiet arithmetic of evolution. The first hunters did not know they were predators, just as the first prey did not know they were being hunted. It was all a matter of chance and survival, repeated endlessly across generations until movement became pursuit, and feeding became predation. The Cambrian Period began roughly 541 million years ago, and in geological terms, it was like the opening act of a great performance. Life exploded in diversity. In only a few tens of millions of years, almost every major animal body plan we know today emerged in some form. It's easy to think of this as sudden, but even a so-called explosion in deep time happens over spans so vast that entire mountain ranges could rise and erode while it unfolds. Still, compared to the quiet billion years before it, the Cambrian was a storm of invention. Creatures began to grow hard parts, shells, spines, armour. Others developed eyes, limbs and strategies, and as soon as one creature learned to protect itself, another evolved to overcome that protection. Evolution had discovered escalation, and from that point onward, the oceans would never again be peaceful. If we could stand on the seafloor then, we would see landscapes unlike anything familiar. Instead of coral reefs, there were mats of bacteria and soft algae. The water might have seemed cloudy with silt and plankton. Strange shapes moved through it, many of them gliding close to the bottom. Some looked like flattened worms, others like small armoured pancakes with legs. Nothing had yet learned to swim powerfully in the open water. The world of the Cambrian was a realm of crawlers, drifters, and gliders, each adapting to a new and unpredictable environment. And within this emerging ecosystem, the first true hunters appeared. It's important to remember that the word hunter doesn't mean large or fierce, at least not yet. In the Cambrian seas, being a hunter could simply mean having a mouth capable of gripping, a body capable of moving toward prey, and senses keen enough to know when to strike. Many early predators were small, some less than a centimetre long. They prowled through mats of microbes, searching for softer creatures to ingest. One of the earliest examples might have been the tiny organisms known as preapulid worms, simple tubular bodies that used a retractable feeding organ to grab unsuspecting prey. Primitive as they seem, they mark the beginning of something monumental. The first time one living thing actively sought another for food. That shift from passive feeding to active hunting reshaped evolution itself. For every predator that appeared, there had to be a response. Some creatures developed shells of calcium carbonate, fragile but enough to resist a soft-bodied attacker. Others flattened themselves against the seabed, blending with sediment. Some grew spines or secreted toxins. Each adaptation forced the other side to improve. Eyes became sharper, limbs faster, shells thicker. Within only a few million years, the arms race of life had begun in earnest, and the oceans became laboratories of innovation. Among the many strange and wonderful creatures of this time, one stands out for what it represents rather than just how it looked. Imagine an animal with a soft segmented body, each segment lined with small flaps used for swimming. Its head bears two large compound eyes far more sophisticated than anything else of its era, and from its mouth extend a pair of grasping appendages shaped like the claws of a shrimp. This creature could grow to nearly a metre in length, enormous compared to most Cambrian life. It was agile, fast, and perfectly designed to capture smaller animals drifting through the sea. Its name, given much later, is Anomalocaris, meaning strange shrimp, and in many ways it was the ocean's first apex predator. But we'll come to Anomalocaris soon enough. For now, imagine the smaller steps that made its existence possible. The evolution of vision, for instance, was one of the most significant changes of the Cambrian. Before eyes, life depended on touch and chemistry to find food or avoid danger. Once light became a source of information, everything changed. An animal that could see could plan, could orient itself, could chase. The emergence of eyes triggered an evolutionary cascade. Predators evolved better sight to locate prey, and prey evolved ways to hide. The interplay between seeing and being seen drove an explosion in body forms and behaviours. In that sense, the first glimmer of vision was also the spark that ignited the age of predators. In these ancient seas, size did not always dictate power. Trilobites, among the most recognisable Cambrian animals, were abundant and diverse. Many crawled slowly over the sediment feeding on detritus, but some species became active hunters, equipped with spiny limbs and sharp mouth parts. They patrolled the seafloor like armoured beetles, overturning debris in search of worms and small-shelled creatures. Their hard exoskeletons left behind some of the most detailed fossils in existence, giving us an intimate look at their anatomy, and even the traces of their compound eyes. For nearly 300 million years, trilobites would dominate marine ecosystems, a lineage that began in those same Cambrian waters where hunting first took shape. The Cambrian oceans were also home to a multitude of experiments that didn't last. Evolution is a process of trial and error, and for every successful design like the trilobite, there were dozens that vanished without descendants. Some animals combine traits in ways that seem almost absurd to us. Long-stalked eyes, soft bodies with stiff plates, feathery limbs used for both swimming and breathing. Others floated upside down or moved sideways, navigating in ways that seemed to ignore the rules of balance. To them, there were no rules. only what worked long enough to reproduce. In that sense, the Cambrian was less a stable ecosystem and more a vast creative workshop where nature tried every idea at once. When we look at the fossils today, often preserved in exquisite detail in deposits like the Burgess Shale of Canada or Chengjiang in China, it's easy to forget that these were once living, moving beings. Each left faint trails in the sediment, each breathed the same water, and each played its part in the grand experiment that would one day lead to vertebrates, fish, and eventually us. But back then, none of that was destined or planned. The story of a life has no script, only momentum. The predators of the Cambrian were simply following opportunities, adapting moment by moment to a changing world. If you listen closely to the story locked within those rocks, you can almost sense the rhythm of it, the endless repetition of change, competition, and adaptation. Not as poetry, but as a kind of biological logic. When one form found success, it multiplied. When it faltered, another took its place. The ancient seafloor became crowded with burrows, trails, and discarded shells. Above them, swimmers glided through the dim light, chasing or fleeing, feeding or hiding. For the first time in Earth's history, survival depended on more than simply existing. It required awareness, reaction, and strategy. And yet, for all its novelty, the Cambrian world was fragile. The oxygen levels of the oceans were still stabilizing. Volcanic activity could alter chemistry overnight. Extinction was as common as emergence. Each new hunter pushed the system further toward complexity, and that complexity brought vulnerability. Still, the balance held long enough for evolution to take root in its new direction. In those uncertain seas, the blueprint of modern ecosystems was being written, not by design, but through constant feedback between predator and prey. As we drift through this vision of the early oceans, it's worth pausing to imagine the silence of it all. There were no fish yet, no coral reefs echoing with clicks and calls, no sound of waves breaking on beaches lined with vegetation. Just the slow pulse of water, the faint stirring of limbs in silt, and the subtle shimmer of plankton drifting through sunbeams. In that hush, life's first hunters moved with purpose newly invented. Their legacy would ripple forward through every age to come. This was the dawn of pursuit, the first stirring of a chain of events that would eventually fill the seas with sharks and dolphins, the skies with birds, and the land with predators of every shape. It all began here, in the dim Cambrian light, when life learned not just to exist, but to chase. The world was ready for its next transformation, and deep within those waters, something extraordinary was beginning to unfold. Long before the seas filled with jaws and the sharp certainty of predation, the ocean floor was a quiet and almost gentle place. It wasn't empty, far from it, but the life that covered it had no real need for speed or violence. Everything moved slowly, gliding through mud or floating along with the current, feeding in silence. For hundreds of millions of years, that pace was enough. Energy came from sunlight filtered through the water and from organic matter sinking from the surface. Nothing had yet imagined teeth or claws or the intent to chase. To live was to drift, to feed, and to divide. That simplicity defined the planet's earliest oceans. Imagine standing on a shore that does not yet know plants or the colour green. The land stretches barren, bare rock and sand, occasionally darkened by thin microbial mats that cling to moisture. The air carries no sound but the wind, no scent but minerals. Ahead, the ocean breathes under a pale blue sky. At the surface, faint ripples catch the light of a sun still slightly dimmer than today's. Beneath, an entire world waits, alien yet alive, a realm of soft bodies and uncertain shapes. If you could dive into those waters, you wouldn't see anything large. The first ecosystems were microscopic tapestries of algae, bacteria, and single-cell drifters. They form the scaffolding of life, transforming light and minerals into energy, building oxygen, and setting the stage for what would come next. Down in the shallows, a layer of fine sediment blanketed the seafloor. Across it stretched colonies of cyanobacteria, creating sticky mats that trapped particles of sand and silt. These microbial carpets were among the oldest living communities on Earth, and in many ways they still are. Their modern descendants survive in tidal flats and lagoons, quietly continuing a process that began more than 3 billion years ago. On top of these mats moved small, soft-bodied animals, early worms, sponges and other creatures that left only the faintest traces of their existence. Many burrowed into the sediment, feeding on the organic matter buried within. Others filtered water, drawing in tiny food particles and expelling waste. The entire ecosystem operated on recycling and patience. Nothing hunted, nothing fled. But even in that slow rhythm, something was changing. Multicellularity had given organisms new possibilities. Instead of being confined to a single task, they could specialize. Some cells became stronger, forming muscle-like tissue. Others developed sensitivity to chemicals, temperature, or touch. Small as they were, these new creatures could now respond to their surroundings in more complex ways. Over millions of years, that sensitivity became coordination, and coordination became movement. The still world began to stir, not yet in pursuit, but in exploration. The Precambrian seas were ruled by simple physics as much as biology. Water moved in steady cycles, currents shaped by tides and temperature. The light that penetrated the upper layers of the ocean was the fuel of everything below, and in that delicate balance, early ecosystems found stability. Yet stability in nature never lasts forever. Whenever one form of life becomes dominant, it creates pressure for another to adapt. The vast microbial mats that covered the ocean floor were both cradle and buffet. They provided habitat, but they also offered abundant food for any organism that could find a way to graze effectively. The first animals to do so, perhaps small slug-like grazers with rasping mouthparts, were the early disruptors of that quiet world. Fossil evidence for this period is sparse but telling. In formations like the Ediacara Hills of Australia, impressions of soft-bodied creatures remain preserved in ancient sandstone. They bear no resemblance to modern animals. Some look like quilts, some like fronds, some like rings pressed into the mud. For decades, scientists debated what they even were, plants, fungi or animals. Today, most are thought to represent early experiments in animal life. These Ediacaran organisms lived in a time before hard shells, before skeletons, before anything resembling the predators that would define the Cambrian. Their bodies were fragile, but their persistence shaped the ecosystem that followed. The Ediacaran world ended gradually, not with disaster, but with transition. As oxygen levels in the oceans rose and nutrients became more abundant, life grew more active. The chemistry of the planet itself changed, paving the way for biological innovation. It was during this time that the genetic toolkit for complex animals developed, the genes that would later give rise to eyes, limbs, and nervous systems. Though nothing yet had teeth, the blueprint for building them was quietly assembling in the DNA of simple creatures drifting through those early waters. The idea of a world without predators is difficult to imagine. We live surrounded by competition, where every ecosystem is defined by who eats whom. But before the Cambrian, the concept of predation didn't exist. Organisms absorbed, grazed, or filtered. Energy moved slowly through the web of life. A sponge could live unbothered, growing steadily on the seafloor, feeding on microscopic particles carried by the current. Worms could burrow without fear of being chased. The absence of danger shaped evolution just as much as its later presence would. Without threats, creatures could afford to be soft, slow, and exposed. Still, evolution does not recognize peace as an endpoint. Given enough time, any imbalance creates an opening for change. the soft-bodied world, rich with unprotected life, was an opportunity waiting to be exploited. Somewhere in those ancient sediments, a lineage of animals began to develop structures that allowed for grasping and tearing. They were not yet jaws, but flexible, muscular openings that could close and hold. It was a simple change, but profound. The ability to capture another organism instead of simply absorbing detritus introduced a new way to survive. Those that could do it gained access to concentrated energy and nutrients, and that advantage drove further refinement. One of the first clues to this new behaviour comes from trace fossils, burrows and tracks left in the sediment. Around the boundary between the Ediacaran and Cambrian periods, these traces become deeper, more complex, more directed. Instead of meandering randomly, some burrows follow purposeful paths, intersecting the remains of other organisms. This suggests active searching. Something was moving through the mud not just to hide or feed passively, but to find specific targets. It's in these silent tracks that we see the first hints of the hunter's mindset taking shape. To understand how radical this was, consider that for billions of years, life had followed a simple rule. Energy flowed from the sun to producers, from producers to decomposers, and then back into the environment. Now a new channel opened, one in which animals consumed other animals. Energy could move up levels, creating hierarchies and dependencies. This restructured ecosystems entirely. Suddenly, the size and behaviour of one species affected many others. The emergence of predation was not just a biological milestone, it was an ecological revolution. Of course, none of this happened overnight. For millions of years, the line between grazer and predator was blurred. Many early animals fed by sifting through detritus and occasionally ingesting something still alive. Some used simple suction to draw food into their bodies, others used tiny appendages to grasp particles, but as sensory systems improved, so did accuracy. Once an animal could detect movement or chemical cues from prey, selective hunting became possible. That step marked the beginning of an entirely new kind of relationship in nature, one defined by pursuit, defense, and adaptation. The ocean of that era was a mosaic of habitats. Shallow waters near continental shelves teemed with microbial life, while deeper zones remained dark and still. The chemistry of these layers dictated who could live where. Early hunters likely favoured the margins, where light and nutrients met. It was in these transitional regions that complexity thrived. Evolution loves the edges, where stability meets change, where old rules begin to bend. The pre-Cambrian seas were full of such edges, both literal and biological. In this environment, the foundation for all future predators was built. Muscles grew stronger, nervous systems became more connected, sensory organs became more refined. What had once been simple reflexes evolved into coordinated behaviour. By the time the Cambrian period officially began, the seas were primed for an explosion of diversity. The pieces were already in place: mobility, perception, digestion, and competition. All that remained was for nature to combine them in new and unexpected ways. When we look back on that world now, it feels strangely serene. No roaring, no sudden strikes, no struggle. Just the slow choreography of evolution unfolding in silence. Yet beneath that calm surface, potential was accumulating. The absence of predators was not an endpoint, but a vacuum, and nature abhors a vacuum. The first creatures to break the peace would unleash forces that still shape life today. The development of hunting did not simply add danger, it added direction. From that moment on, survival would favour the alert, the swift, and the adaptable. It's tempting to think of this as a loss of innocence, but life does not operate by moral measure. The invention of predation was as natural as the invention of photosynthesis. Both are solutions to the same problem: how to use energy efficiently in a changing environment. What shifted was not purpose but method. The ocean learned to recycle energy through its own inhabitants, instead of relying solely on sunlight and decay. In doing so, It accelerated the pace of evolution, turning a slow chemical drift into a dynamic, interconnected web. Every modern predator, from a dragonfly to a blue whale, traces its lineage back to this transition. The very idea of movement with intent, the chase, the strike, the strategy, originated in the soft shadows of those early seas. Even the simplest reflex you have today, the impulse to reach out and grasp, carries echoes of that same evolutionary moment. It was the dawn before the dawn, the moment before the Cambrian truly bloomed. As the clock of deep time turned and oxygen levels rose higher still, the gentle equilibrium of the Precambrian oceans began to shift irrevocably. Shells appeared. Eyes evolved. The silt that once held simple burrows now recorded complex interactions. The world was about to awaken in full, and the quiet age before teeth was ending. Far below the surface, unseen and unnoticed, the hunters were already coming to life. The turning of the Earth 540 million years ago marked a transformation so profound that it still defines everything alive today. The seas that had once been dim and still began to shimmer with movement, colour and form. What had been a quiet garden of simple creatures erupted into an experiment of almost reckless creativity. The Cambrian Period arrived, and with it came the first great diversification of animal life. The ocean, which had been a tranquil reservoir of soft shapes and slow grazers, suddenly became crowded. Bodies grew larger, stranger, and more complex. This was not a sudden explosion in the human sense of the word. It took millions of years. But in the scale of evolution, it was as if the planet itself had drawn a deep breath and awakened. In the sediments of what would one day be Canada, China, Greenland, and Australia, fossils capture the evidence of this awakening. Layer upon layer of fine mud hardened into stone, preserving ghostly outlines of creatures that lived and died in those early seas. Some resemble familiar forms, worms, arthropods, sponges, but others defy easy classification. They are the evolutionary equivalents of sketches, prototypes, ideas in progress. The Cambrian was an age of experimentation, and nature had no shortage of imagination. Legs appeared, eyes appeared, jaws, shells, segments, and spines, each invention branching into new possibilities. For the first time, ecosystems became dynamic, with multiple layers of predators, prey, and scavengers all interacting in ways that had never existed before. At the start of this period, much of Earth's surface was covered in shallow seas. The continents were smaller and scattered closer to the equator, where sunlight and warmth encouraged photosynthesis. Oxygen levels were rising, though not yet near modern levels, and the chemistry of the oceans was shifting towards stability. These conditions created fertile ground for innovation. Evolution thrives where the environment provides both opportunity and pressure. In the Cambrian, those two forces worked together perfectly. Organisms had access to abundant resources, but they also faced increasing competition. The result was an evolutionary arms race that transformed the planet. To understand the scale of that transformation, it helps to think about what evolution really is. It's not a ladder or a plan. It's a constant series of small changes, each tested by the simple question of survival. Those that work persist, those that don't vanish. For most of Earth's history, the changes had been slow and subtle. The genetic experiments of early life produced incremental improvements, better ways to capture sunlight, digest nutrients, or resist environmental stress. But once multicellular organisms began interacting directly, feeding on one another, competing for space and resources, evolution shifted gears. Natural selection became faster, more responsive. Each new trait could spark a cascade of adaptations across multiple species. The Cambrian was the first time life responded not just to its surroundings, but to itself. One of the most significant developments was the emergence of skeletons. Until then, most creatures had been soft-bodied. leaving only faint impressions behind. But during the early Cambrian, animals began producing hard parts: shells, plates, spines, and tubes. These structures provided protection against attack, but they also allowed new forms of movement. Muscles could anchor to rigid supports, enabling stronger contractions and more controlled motion. The diversity of shapes expanded dramatically. Some species grew long armoured tubes and lived fixed to the seafloor. Others developed jointed exoskeletons and legs for walking. The interplay between defence and mobility set off a feedback loop that would define marine life for the rest of Earth's history. The fossil record of this time tells a story not of gradual improvement, but of sudden variety. Within a relatively short span, we see the ancestors of almost every major animal group appear: arthropods, mollusks, echinoderms, and even the early forerunners of vertebrates. It's as if evolution had opened a floodgate of possibilities and let them all run at once. For scientists, this rapid diversification remains one of biology's great puzzles. What exactly triggered it? Several factors likely work together: rising oxygen, new ecological interactions, and the genetic flexibility that came from a recently evolved set of developmental genes. These genes, which control how body plans are organised during growth, allowed evolution to rearrange existing structures in creative ways. A limb could become a fin, an antenna, or a jaw, depending on subtle changes in timing and expression. The genetic foundation for complexity had finally matured, and the environment provided the stage. If we could visit those oceans now, we might struggle to recognise them as part of the same planet. The water was shallower, the light softer, the atmosphere thinner. Yet beneath the waves it was teeming with activity. Trilobites scuttled over the seafloor in search of food, their jointed legs stirring up clouds of sediment. Small worm-like creatures burrowed through the mud, leaving winding trails behind them. Above them swam forms so unusual they seem almost alien. Fan-shaped swimmers, disc-bodied drifters, and long ribbon-like animals that undulated through the current. Every niche was being filled for the first time. There were grazers feeding on microbial mats, scavengers cleaning up remains, and predators stalking through the water column. The Cambrian marked the birth of the modern ecosystem. Among the many inventions of this era, perhaps none was more transformative than vision. Before the Cambrian, the sense of sight had been rudimentary at best, simple light-sensitive patches that could detect brightness but not shape. Now, true eyes appeared, capable of forming images. The first compound eyes, made of dozens or hundreds of tiny lenses, gave their owners the ability to perceive motion and direction with remarkable precision. This single development reshaped evolution almost overnight. With sight came awareness, and with awareness came strategy. Animals could now recognize potential mates, avoid obstacles, and track moving prey. The interplay between hunter and hunted intensified dramatically, driving further adaptations in both offense and defense. The emergence of eyes also changed how creatures interacted with their environment. Brightly coloured shells and patterns evolved, perhaps as camouflage, perhaps as display. Some animals used transparency to disappear into the water, while others developed hard carapaces that reflected or diffused light. For the first time, behaviour became complex. Creatures began responding not only to chemical cues, but to visual signals. A chase could now involve anticipation, pursuit, and evasion. In this sense, the Cambrian wasn't just a biological revolution, it was a sensory one. Another innovation that reshaped the seas was the development of more efficient movement. Early animals had relied on cilia or simple muscle contractions to glide or crawl, but as bodies became more specialised, locomotion became a key factor in survival. Some creatures evolved paired appendages that acted as paddles, others developed flaps or fins that generated lift. These improvements turned the seafloor from a static surface into a three-dimensional environment where animals could move vertically as well as horizontally. The ocean became layered not just by depth and temperature, but by activity. Hunters could now patrol the mid-water zones, and prey had new spaces to hide. While all this innovation brought diversity, it also brought risk. The more specialized an organism became, the more dependent it was on its particular niche. Environmental shift could wipe out entire lineages. The Cambrian seas were unstable, subject to fluctuations in temperature and chemistry. Extinctions were common, but so were new arrivals. In the constant cycle of loss and renewal, evolution advanced by experiment. The failures of one species created openings for others. The fossil record captures this restless energy, frozen moments of adaptation in motion. The Burgess Shale, discovered high in the Canadian Rockies, provides one of the clearest windows into this world. Its fine-grained sediments preserved even the soft tissues of ancient animals, revealing details that would otherwise have vanished. There we see creatures like Opabinia, with 5 eyes and a long flexible proboscis tipped with a claw. There is Hallucigenia, a spindly organism that walked on needle-like legs with rows of spikes running down its back. And there is Wiwaxia, covered in overlapping scales and spines, part mollusk, part mystery. Each of these animals represents an evolutionary pathway that was explored and in most cases abandoned. But collectively they demonstrate the Cambrians' defining trait: possibility. For the first time, nature had the tools to explore complexity. It was no longer limited to single solutions. The same biological building blocks could be rearranged endlessly, producing diversity without bound. That flexibility would prove essential for the long-term resilience of life. Even as most Cambrian species disappeared, their genetic innovations lived on, inherited and repurposed by future generations. The limbs of trilobites would become the model for crustaceans and insects. The armour of early mollusks would evolve into the shells of snails and clams. The primitive notochord found in early chordates would one day become the backbone of fish, reptiles, birds and mammals. The Cambrian was the beginning of that lineage, a branching tree that would fill the oceans, the skies and eventually the land. It's easy to imagine this era as chaotic, but it had its own balance. Each new adaptation triggered countermeasures. When shells appeared, some predators developed crushing limbs. When speed increased, so did stealth. Evolution's constant exchange of innovation and response created a dynamic equilibrium that kept ecosystems both stable and flexible. This balance has persisted for 500 million years, through countless extinctions and recoveries. It began in those ancient seas when life first learned to compete with itself. For modern scientists, the Cambrian period offers insight not only into where we came from, but into how innovation works. Complexity doesn't arise from a single leap, but from countless small steps interacting over time. The Cambrian awakening was not a miracle. It was a natural outcome of life reaching a threshold of diversity and connection. Once evolution had enough ingredients to work with, creativity became inevitable. Each organism was both participant and product of the process, shaping its world even as it was shaped by it. In that sense, the Cambrian teaches us something subtle about progress. The appearance of predators, the development of eyes, the rise of shells. All these events seem dramatic, but they are the accumulation of countless small adjustments. Change is not sudden at the scale of a single life, but across millions of years it becomes transformation. Every ripple on that ancient seafloor contributed to the ocean we know today. The awakening of the Cambrian was not just about survival. It was about awareness, about the first glimmers of interaction that went beyond mere reaction. A creature sensing another's movement, responding not by instinct alone but by memory and pattern recognition. That was the beginning of behaviour. The biological machinery of neurons and senses was assembling the capacity for curiosity. In a very distant way, those early hunters and their prey set the stage for perception itself. As the eons passed, the diversity of life deepened. The oceans grew crowded with forms that grazed, hunted, scavenged and hid. The first complex food webs emerged, linking thousands of species in a single tapestry of energy exchange. The seas that had once been quiet and slow now pulsed with vitality. The age of passive existence was over. Life had awakened to itself, and nothing would ever return to stillness. The world that rose from this awakening was vibrant and volatile. The predators that would soon dominate it were already evolving in miniature, the precursors of trilobites, the ancestors of Anomalocaris, the early arthropods testing new ways to move and feed. They were small, but the blueprint for power was there. Soon, the arms race of the Cambrian would reach its peak, and the first true marine hunters would rule the seas. The stage was set, the actors assembled, and the drama of predation was about to begin in earnest, deep in those restless waters where the story of life's hunger first took shape. When light first met vision, the world changed forever. Before that moment, life had existed in a kind of sensory fog, guided only by touch and chemical traces. The oceans were a place of gradients, warm and cold, light and dark, nutrient-rich and barren, but none of their inhabitants truly saw them. They felt the world through proximity, through molecules drifting in the water, through vibration and contact. Then, somewhere in those ancient shallows, the chemistry of sensation evolved into something far more powerful. Photoreceptive cells, molecules that reacted to light, began to cluster and organize. The first eyes were not eyes as we know them. They could not form images or detect shapes. They were patches of pigment, shallow cups that simply distinguished light from darkness. But that distinction changed everything. The Cambrian seas were already crowded with motion by the time vision began to spread. Organisms moved through the water in search of food, partners, and safety. Until this point, encounters between species were mostly accidental, determined by the random movement of currents. But light offered a new kind of information. It allowed direction. An animal could now orient itself toward brightness or away from shadow. For the first time, life had a way to map its surroundings beyond touch. The earliest creatures to develop this sense gained an enormous advantage. They could find food faster, detect movement sooner, and avoid becoming a meal themselves. Evolution wastes nothing once it finds a useful tool, and so vision spread rapidly across the oceans. The origin of eyes was not a single event, but a cascade of improvements built upon simple beginnings. Photoreceptors grouped together, forming curved surfaces that could detect the angle of incoming light. A shallow depression became a cup deepened into a pit, and the pit grew a narrow opening that improved resolution. Eventually, transparent layers formed to protect these delicate organs, and primitive lenses evolved to focus light more effectively. Each step, small on its own, compounded over time. What began as a faint shimmer of awareness became the ability to see. The fossil record gives us a few glimpses of this transformation. Among the earliest creatures with true eyes were trilobites, those iconic segmented arthropods that crawled across the Cambrian seafloor. Their eyes were compound, made up of hundreds of tiny lenses, each a perfect piece of natural engineering. Under magnification, they resemble a honeycomb of crystal domes, each one capturing light from a slightly different angle. This mosaic of inputs formed a single, panoramic view of the world, a vision suited not for beauty but for precision. Trilobite eyes were made of calcite, a mineral that also formed their exoskeletons. They were literally stone eyes, grown from the same material that protected their bodies. Hard, durable, and ancient, they allowed these creatures to detect predators and prey alike in a way that nothing before them could. But trilobites were not alone in this visual revolution. Other arthropods, soft-bodied or partially armoured, developed similar systems. Anomalocaris, one of the largest and most formidable hunters of the time, possessed a pair of enormous compound eyes mounted on stalks. Each eye contained tens of thousands of lenses, granting it exceptional resolution. In modern terms, its eyesight may have rivaled that of a dragonfly, among the best visual systems nature has ever produced. Imagine that for a moment. In a world where most animals were still groping blindly through the dark, a meter-long predator was gliding through the water with crystal eyes capable of detecting the faintest flicker of motion. It could spot prey from a distance, adjust its path, and strike with precision. In a very real sense, sight created the predator as we understand it. The emergence of vision transformed not only how animals hunted, but how they lived. Light became a form of communication. Colours, patterns, and movements gained new meanings. Some creatures evolved reflective surfaces to confuse or dazzle attackers. Others used pigmentation for camouflage, blending into the silt or the dim green light near the seafloor. The arms race that began with movement now expanded into perception. To be seen was to be vulnerable. To see was to hold power. Every improvement in sight demanded an equal improvement in concealment. It was a dialogue that has never ended, continuing today in every ecosystem from coral reefs to forests. It's easy to underestimate how profound this change was. Before sight, time in the ocean moved slowly. Events unfolded at the pace of diffusion and drift. But once animals could see, reaction became immediate. The tempo of life accelerated. A shadow passing overhead could trigger escape. A flash of motion could draw pursuit. The ocean became dynamic not only in biology but in behaviour. Each encounter between species carried new complexity, new possibility. The Cambrian world was learning to act and react in real time. For scientists studying the early evolution of eyes, there is no single fossil that marks the exact transition from light sensitivity to vision. The process was too gradual, too varied. But we can infer much from modern biology. Many of the same genes that build eyes in humans are present in animals that diverged hundreds of millions of years ago. These conserved genetic patterns suggest that the foundations of vision evolved once and were then modified repeatedly. In other words, the ability to see did not evolve separately in every lineage. It began early, perhaps in a common ancestor of all animals that possessed nerve tissue, and was elaborated upon in countless ways. The Cambrian simply represents the point where vision reached its first true sophistication. An organism with eyes could no longer rely on the cover of darkness or stillness alone. It needed new defences. Hard shells, spikes, and burrowing behaviours all intensified during this time. The fossil record shows a sudden proliferation of animals capable of digging or retreating into protective casings. Even soft-bodied species began to cluster in groups or hide within the shadows of larger structures. Light forced life to adapt to being observed. It also created the concept of distance, of being able to detect something not yet within reach. This single shift in perception laid the groundwork for complex behaviours like stalking, pursuit, and coordinated escape. The emotional analogues of fear and focus that drive modern animals trace their origins to this sensory awakening. For the predators of the Cambrian, vision was both a weapon and a guide. The hunter could now make decisions based on visual cues, estimating direction and distance before attacking. This required not only eyes, but a nervous system capable of processing information quickly. The development of improved vision likely drove parallel changes in brain structure and muscle coordination. With each generation, the connection between sight and movement deepened. The ability to perceive detail was meaningless without the ability to respond to it. Over time, evolution fused the two, creating creatures capable of deliberate targeted motion. The chase, as a concept, was born. The introduction of sight also changed how organisms related to their environment. Many began to rise off the seafloor, exploring open water where light was strongest. The dim, sediment-filled shallows remained home to those that preferred concealment, but others took advantage of clarity and speed. The vertical dimension of the ocean, previously underused, became a new frontier. With vision guiding them, swimmers could orient themselves to the direction of light, following it upward or away depending on need. Some may have used it to regulate depth, avoiding predators or tracking plankton blooms. Light became a map, and those who could read it thrived. When we reconstruct this world through fossils and computer models, the picture that emerges is one of remarkable subtlety. Eyes did not make the ocean simply more violent, they made it more aware. Every organism became part of a network of signals, shadows, flashes, colours, movements, each influencing the other. Predators learned to ambush from below, using the brightness of the surface to mask their approach. Prey learned to scatter when light patterns changed. These interactions gave rise to behaviours that still dominate marine life today. Schooling fish, darting crustaceans, stalking cephalopods, all are echoes of strategies first explored in the Cambrian's illuminated seas. There is another, quieter consequence of vision that is easy to overlook. Eyes created the possibility of memory. To navigate visually, an animal must recognise patterns, shapes, contrasts, sequences of light and shadow. This required neural networks capable of comparing what was seen now to what was seen before. In that comparison lies the seed of memory, and with memory comes learning. An animal that remembered the shape of a predator or the location of shelter would survive longer than one that did not. Over countless generations, this favoured creatures with more sophisticated nervous systems. The path from simple vision to cognition began here, in these same ancient waters where the first eyes opened. The Cambrian Ocean, therefore, was not only a theatre of survival, but of perception. Each species experienced its world differently depending on how it saw or didn't see. For some, light was a danger to be avoided. For others, it was a tool, a weapon, or even an invitation. The diversity of eyes reflected the diversity of lifestyles. Some were large and mounted on stalks, scanning the horizon for movement. Others were tiny pinpoints embedded in the body, detecting only the faintest shifts in brightness. There were no standards yet, no single solution to the problem of sight. Evolution was still testing, comparing, refining. Among the many wonders of the Cambrian, the variety of visual systems stands out as a microcosm of evolution itself. Each adaptation opened new ecological possibilities. A predator with forward-facing eyes could judge depth and strike accurately. A prey animal with eyes on the sides of its body could watch in all directions at once. Those advantages reinforced behaviours and body plans, driving further divergence. Over time, sight didn't just change how creatures survived, it changed what they became. It's humbling to think that the ability to see, something so integral to our own existence, began as a small patch of pigment in a creature no larger than a fingernail. That simple adaptation, replicated and refined, turned the oceans from featureless darkness into a world of forms and motion. It allowed life to perceive itself, and, in doing so, to interact in ways that would lead to intelligence. Every glance, every moment of awareness that any living being experiences today owes a debt to those first eyes that saw. Even now, when scientists study modern arthropods or worms with simple photoreceptors, they are peering back in time. The same proteins that capture light in their retinas are ancient molecules, virtually unchanged since the Cambrian. They are biological fossils, living reminders of an age when sight was new and fragile. Each time an organism reacts to a shadow or turns toward a glimmer, it reenacts that ancient discovery. The evolutionary thread connecting then to now is unbroken. The rise of vision marked the true awakening of interaction in the ocean. It gave shape to fear and opportunity alike. For the prey, light became something to hide from. For the predator, it became a guide. The seas shimmered not just with sunlight but with purpose. Movement gained intention, and the silent ballet of evolution accelerated. The world was no longer simply inhabited, it was watched. As the Cambrian continued, those that mastered vision began to dominate. Eyes grew larger, more complex. Nervous systems expanded to process the flood of information. The relationship between seeing and surviving tightened until they became inseparable. The first hunters with vision changed the evolutionary landscape, driving prey to invent armour, burrows, and speed. every adaptation built upon the last, each step feeding the next. In that cascading sequence of innovation, a new balance emerged. Light no longer meant safety or danger by itself. It meant information, and information meant power. The creatures that could use it most effectively would come to define the seas. The Cambrian world had entered its age of sight, and from that moment on, the history of life would never again return to darkness. Beneath those rippling waves, the first eyes continued to open. They watched the shadows of swimmers gliding through dim light. They saw movement where before there had only been murk. And somewhere in that flicker of awareness, the story of perception began to unfold, leading toward a future where every glance, every decision, every spark of understanding could trace its lineage back to that first act of seeing in the ancient Cambrian Sea. Long before the Cambrian seas were ruled by giants, the first true hunters were small enough to fit on the tip of a finger. Their world was a landscape of sediment grains and bacterial mats, a vast wilderness measured in millimeters. Yet within that confined scale, a revolution in behavior was unfolding. These creatures did not drift passively or wait for nutrients to come their way. They sought. They followed chemical trails, sensed vibration, and moved with intention. They were the first animals to chase living prey, and in their tiny bodies the logic of the predator was born. The Cambrian period was still young when these miniature hunters began to thrive. The ocean at that time was layered with opportunity. Plankton floating near the surface, algae coating rocks, detritus accumulating in the shallows. Everywhere was food if one knew how to reach it. The first grazers and scavengers had already transformed the ecosystem by disturbing microbial mats and breaking down organic matter, but they had also created a new niche: prey. To feed on another animal was a new concept, and it carried immense evolutionary potential. The energy locked inside living tissue was dense and efficient. A creature that could capture it gained far more than one that sifted endlessly through debris. Among the earliest known predators were the priapulid worms, small tubular animals equipped with an extendable proboscis lined with spines or teeth-like structures. These weren't jaws in the modern sense, but they served the same purpose: gripping, pulling, and consuming. Priapulids burrowed through the soft seafloor, emerging to grab unsuspecting prey, often smaller worms or larvae. Their fossils, found in formations such as the Burgess Shale and the Sirius Passae in Greenland, show that they were already well adapted for a life of ambush. Some species grew only a few centimeters long, yet they represent a profound shift in the history of life, the transition from passive feeding to active predation. The mechanics of their hunting were simple but effective. A priapulid would extend its introvert, a muscular feeding organ covered in hooks, to seize and retract prey into its digestive tract. The process was slow by modern standards, but in the Cambrian Ocean, where reflexes were still primitive, it was devastatingly efficient. Once caught, there was no escape. In those tiny encounters beneath the sediment, evolution was discovering the blueprint for every predator that would follow. Muscles coordinated with nerves, movement with perception, and feeding with action. As these small predators multiplied, the seafloor became a more dangerous place. Soft-bodied creatures that once roamed freely began to develop defensive strategies. Some evolved thicker cuticles or simple external skeletons. Others learned to burrow deeper or move faster. The balance between offense and defense, once almost non-existent, became a central force shaping evolution. The competition at this scale was fierce, and each new adaptation spread quickly through the gene pool. Trilobites, the iconic inhabitants of Cambrian seas, began their rise during this time as well. Many were scavengers or grazers, but some smaller species may have turned to opportunistic hunting. Their segmented bodies and jointed limbs gave them agility that few of their contemporaries could match. Trilobites with spiny appendages and specialized mouthparts could stir the sediment to uncover worms and soft-bodied prey. Fossilized trackways show evidence of pursuit, trails that curve or double back suggesting directed movement rather than random wandering. To modern eyes, these patterns might look like the meandering of a beetle across sand, but in them lies the first hint of deliberate behaviour in marine life. The world of these small hunters was not only one of movement but of sensing. Chemical detection was perhaps their most important tool. Long before sight dominated, molecules in the water served as messengers. A wounded organism released a trail that could be followed. A patch of decaying material announced opportunity. Some predators used fine sensory hairs or cilia to read these invisible cues, tracing them back to their source. Even the simplest nervous systems could interpret gradients, stronger here, weaker there, and adjust direction accordingly. This ability to orient toward a goal was the beginning of purposeful navigation. Predation at this scale had unexpected effects on the broader environment. As worms burrowed and hunted, they churned the sediment, mixing oxygen into deeper layers and changing its chemistry. This process, known as bioturbation, altered how nutrients cycled through the ecosystem. In other words, the act of small creatures hunting each other reshaped the ocean floor itself. Over time, this increased oxygen availability for other organisms, creating conditions that supported greater diversity. The relentless appetite of tiny predators indirectly paved the way for the evolution of larger, more complex species. Their world was rich in texture. Imagine the seafloor as a rolling plain of fine silt, dotted with mounds and burrows. The water above is hazy, filled with drifting particles. Sunlight filters down in shifting beams, casting faint shadows across rippling sand. A small priapulid worm moves just beneath the surface, its body undulating as it probes ahead. Nearby, a trilobite passes, its compound eyes scanning the sediment for any sign of motion. Above them, translucent creatures drift lazily, their gelatinous bodies catching the light like glass ornaments. It was a quiet but restless ecosystem, each moment charged with tension between hunger and survival. In this setting, size was deceptive. A creature no longer than a fingernail could dominate its surroundings simply by being faster or more perceptive. Evolution had not yet produced giants, but it had produced efficiency. The advantage lay not in strength, but in strategy. To find prey before being found became the defining rule. The ocean, once governed by chemistry and chance, now ran on awareness. As the Cambrian progressed, diversity increased rapidly. New body plans appeared almost monthly in geological terms. Some of these were minor variations, different limb arrangements, new shell textures, but others introduced entirely novel features. Among them were the first true appendages adapted for grasping. In certain early arthropods, the front pair of limbs became specialized claws or feelers, perfect for capturing small prey. These developments gave rise to a new type of hunter, one that could not only find but manipulate its food. One particularly intriguing animal from this period is Kerygmacula, a slender swimmer with a row of lateral flaps for propulsion and two large grasping appendages at the front of its head. It was small by modern standards, perhaps 20 centimetres long, but it represents a key step toward the sophisticated predators that would later dominate the seas. Its eyes were simple, its movements graceful, and its appetite considerable. It fed on smaller organisms in the open water, marking one of the earliest transitions from benthic hunting along the seafloor to active predation in the water column. Another remarkable creature, Pamdelurion, shared similar traits: a flattened body, flexible lobes for swimming, and delicate appendages for seizing prey. Both animals were early members of a lineage that would eventually produce Anomalocaris, the apex hunter of the Cambrian. In their structure, we see the gradual assembly of the predator's toolkit: mobility, coordination, and sensory precision. Each small refinement brought greater control over the environment, and with it, more efficient feeding. The interplay between these small hunters and their prey set off a chain reaction. As predation intensified, prey species developed tougher exteriors, leading to the widespread appearance of biomineralization. the process by which organisms incorporate minerals into their tissues to form shells and spines. This in turn forced predators to evolve stronger mouthparts and more powerful digestive systems. The result was a feedback loop that accelerated evolution across the entire biosphere. Every meal came at a cost, and every adaptation demanded an answer. Despite their size, these small predators shaped the direction of evolution more profoundly than any giant that would follow. They introduced the ecological dynamics that define life to this day: predator and prey, pursuit and evasion, innovation and response. In their tiny, blind conflicts, nature learned efficiency. Energy began to move through ecosystems faster, driving metabolism, specialization, and complexity. What had once been a slow exchange of nutrients now became a rapid circulation of life and death. For paleontologists, reconstructing this microscopic drama requires patience and inference. Many of the players left no bones, no shells, only the traces of their activity. Burrows, feeding marks, and disturbed sediments tell the story in negative space. In some places, delicate fossils capture the outlines of soft bodies compressed into shale, revealing fine details like proboscises, spines, and appendages. From these, we can imagine how these animals behaved. We can see them as they were, small, determined, endlessly hungry. The abundance of such creatures also meant that they formed the base of new food chains. Larger predators, including the early arthropods, began feeding on them, creating multi-tiered ecosystems for the first time. The simple two-level structure of producer and consumer evolved into a complex web. This complexity in turn supported stability. As more species interacted, energy flowed through the system in multiple directions. When one population declined, another could fill its role. The ocean was learning resilience through diversity. Even at this early stage, behaviours emerged that would later become hallmarks of advanced predation. Some animals hunted cooperatively, following one another's trails through the sediment. Others exhibited territoriality, defending feeding grounds or burrow systems. There is evidence that certain worm species returned to the same burrows repeatedly, suggesting not just instinct but rudimentary spatial memory. The seeds of strategy were germinating, and they would blossom fully in the eons to come. The energy economy of the Cambrian Ocean was astonishingly efficient. Every dead organism became food for another. Every movement stirred nutrients into circulation. Nothing went to waste. In this economy, the smallest predators played a vital role as recyclers, transforming organic matter and fueling the growth of larger life forms. The efficiency of this system ensured that evolution could afford to experiment with new designs. It provided the surplus energy necessary for the rise of complex nervous systems, musculature, and sensory organs. Without those first voracious little hunters, the great apex predators of later eras might never have existed. If one could shrink down and observe this world firsthand, it would look both alien and familiar. Streams of tiny organisms moving with purpose, responding to one another's presence, forming an intricate dance of pursuit and escape. Each interaction lasted only seconds, yet the consequences rippled through deep time. These were the first negotiations of survival, the testing ground where nature refined its most enduring ideas. The Cambrian seas were a theatre of constant motion, but within that motion lay hierarchy. The small ruled by number, by adaptability, by relentless appetite. They did not need to dominate through size because their collective influence was far greater. Every burrow dug, every grain of sediment turned, every organism consumed left an imprint on the world's evolving ecosystems. The ocean's balance depended on their hunger, and so the story of life's great predators does not begin with the mighty or the monstrous, but with the minute. In their small bodies beat the same rhythms that would one day drive sharks through the deep and falcons through the sky. The instincts forged in the Cambrian mud, the impulse to chase, to grasp, to feed, remain within every living creature that hunts today. They were the first to teach the ocean what it meant to hunger, and their lesson would echo forever. The seas that had once belonged to drifters now belonged to seekers. Beneath the rippling light, amid the fine dust of ancient seafloors, a new kind of life had taken hold. It was quick, it was clever, and it was never satisfied. From that restless energy would rise the first true rulers of the ocean, the hunters that would make even the small tremble, the apex forms of the Cambrian seas that would soon arrive to claim their dominion. Long before the ocean was ruled by sharks or reptiles or anything resembling a fish, it belonged to something stranger. In the shifting shallows and darkened slopes of the Cambrian seas, an animal glided that seemed to break every familiar rule of form. Its body was soft yet strong, its movements graceful yet lethal. It was neither worm nor insect nor fish, but something entirely its own. To the small creatures of its world, it was the end of calm and the beginning of fear. Its name, given by humans 500 million years later, was Anomalocaris, the unusual shrimp, though that label hardly captures what it truly was. It was the ocean's first great hunter, an apex predator in a world that had only just begun to imagine what a predator could be. If you could follow one through the Cambrian water, you might first notice how smoothly it moved. Its long segmented body flexed in rippling waves, each segment edged by a pair of flaps that beat in sequence. This undulating rhythm carried it forward with surprising agility. Its large circular mouth, ringed with overlapping plates that opened and closed like the petals of a mechanical flower, pulsed faintly as it swam. From its head extended two powerful appendages, curved and jointed, lined with spines that converged inward like a pair of hooks, designed to snare whatever drifted too close. Above them, a pair of enormous compound eyes surveyed the dim blue world with astonishing precision. It was a creature built not by design, but by the relentless arithmetic of evolution, every line of its body tuned to pursuit. For the animals that shared its habitat, Anomalocaris must have been both a marvel and a terror. Most Cambrian creatures were small and slow, built for grazing, burrowing, or filtering. None were prepared for a hunter that could see them from afar, close the distance in seconds, and tear through soft flesh with crushing force. To the trilobites that scuttled across the seafloor, its shadow would have been the last thing they saw before being lifted from the sediment and drawn into that ring of plates. Its feeding method, though primitive compared to the precision of later predators, was revolutionary. By gripping prey with its appendages and funneling it into its circular mouth, Anomalocaris could process animals too large for simpler predators to handle. It turned the Cambrian seas from a battlefield of small skirmishes into one ruled by power and dominance. The scale of this animal set it apart from everything else. While most Cambrian organisms measured only a few centimetres, Anomalocaris could reach a metre in length. In a world where almost everything was small, it was a giant. Its size alone gave it an advantage, but it was its combination of speed, vision, and control that made it truly formidable. The flaps along its sides worked in perfect coordination, generating lift and thrust. It could hover, surge forward, or glide silently just above the seafloor. Its eyes, each with tens of thousands of individual lenses, could detect movement and shape with clarity unmatched for its time. This was not an animal that relied on chance encounters. It hunted with intent. The fossils that tell its story were for many years misunderstood. Early paleontologists found isolated pieces, appendages that looked like shrimp claws, discs that resembled jellyfish, and segmented bodies that seemed unrelated. It wasn't until decades later that researchers realized they all belonged to the same creature. The revelation that these fragments were parts of a single animal changed how we saw the Cambrian entirely. Before Anomalocaris, scientists imagined the early oceans as populated mostly by small, passive forms. Afterward, they saw a world of interaction, pursuit, and complexity. The Cambrian, once thought to be a tranquil cradle of early life, became a place of drama. The presence of such a predator reshaped the evolutionary landscape. Prey species responded in kind. Trilobites developed thicker exoskeletons, spines, and the ability to roll into tight defensive balls. Some animals began burrowing deeper, escaping the reach of those grasping appendages. Others evolved agility, darting into the water column instead of crawling across the sediment. Every innovation by Anomalocaris forced an answer from its prey, and that cycle of adaptation and counter-adaptation drove the Cambrian explosion forward. The arms race that began at the microbial level now had a master participant, a creature whose very existence compelled change across the biosphere. Its anatomy reveals how specialized evolution had already become. The flaps that lined its body acted much like the fins of modern cuttlefish, creating lift with minimal effort. Small, paddle-like lobes under each flap likely helped it steer with precision. Its head bore a flexible neck region, allowing it to pivot and aim its grasping limbs forward. The mouth parts, once thought to crush trilobite shells, may have been used primarily for consuming soft-bodied prey, though it's possible that Anomalocaris could crack through weaker armour when necessary. Inside its body, a simple but effective digestive tract ran the length of its torso, supported by lateral lobes that may have functioned as primitive gills. Everything about it speaks of efficiency, an organism refined for dominance, yet still alien in every detail. To envision its world, imagine standing on the floor of a shallow Cambrian sea. The light filtering through the water turns everything a hazy turquoise. Clusters of sponge-like organisms sway gently in the current. Worms twist through the silt. Trilobites trudge along, their shells glinting faintly. Then from above a shadow glides by. It moves like a ripple given form, silent but unmistakable. The small creatures react. Some freeze, some burrow, some scatter upward, but for most, there is no escape. The Anomalocaris tilts its body, its eyes locking onto a moving shape below. Its flaps undulate faster, closing the distance. The twin appendages reach forward, flexing open, then snap shut around their target. In one smooth motion, the captured prey is drawn toward the mouth, and the water fills with faint clouds of disturbed sediment. The hunter moves on, leaving only a fading swirl where life once stirred. For modern scientists, Anomalocaris represents a milestone not just in predation, but in the structure of ecosystems. Before it, food webs were relatively flat, composed mostly of primary consumers and detritivores. With its arrival, a new tier appeared at the top, the apex predator. This role introduced regulation, preventing overpopulation of smaller species and maintaining ecological balance. Though such balance was primitive and unstable by modern standards, the principle was the same. Predators like Anomalocaris did not simply consume, they organized life by enforcing limits. In doing so, they shaped the very architecture of the marine world. Its dominance, however, was not eternal. Like all evolutionary experiments, Anomalocaris belonged to a particular moment. Its lineage, the radiodonts, would flourish for millions of years but eventually give way to newer, more efficient hunters. Over time, arthropods diversified into countless forms, some scuttling across the seafloor, others swimming through open water, still others venturing eventually onto land. Yet in each of these descendants, fragments of Anomalocaris persisted. Its segmented body plan, its jointed appendages, its visual acuity, all became foundational elements of later success. It was not the end of a line, but the beginning of one. What made this animal so extraordinary was not its alien shape, but what it represented. The culmination of a chain of evolutionary progress that had begun with microscopic instincts. The first worms that groped through sediment, the early arthropods that developed crude limbs, the creatures that experimented with vision. All of them contributed to the making of this one apex form. In Anomalocaris, the ocean's evolutionary imagination reached a new level of coherence. It was the first organism to embody nearly all the hallmarks of complex predation: mobility, sensory awareness, precision and power. Its eyesight alone was a revolution. The fossilized eyes of Anomalocaris are among the most detailed ever found from the Cambrian. Each compound lens is preserved in three-dimensional relief, showing an optical design so advanced that it rivals those of modern insects. To possess such vision was to command an entirely new relationship with the environment. It could detect movement from meters away, focus on contrasting shapes, and perhaps even distinguish the flicker of shadows cast by other swimmers. For prey animals that had evolved in a world where danger arrived only by touch, this was a nightmare. Sight gave the predator anticipation. It could act before its victims even realized they were in peril. Its method of attack was elegant rather than frenzied. Unlike later hunters that relied on sudden bursts of speed, Anomalocaris used precision and timing. It would drift above the seafloor, scanning for motion. Once it detected a likely target, it adjusted its flaps to generate a burst of acceleration, sweeping its body in a curve that intersected the prey's path. The grasping limbs, jointed like elongated pincers, closed with surprising delicacy, more like a surgeon's tool than a weapon. The captured animal was funneled toward the mouth, where the overlapping plates rotated inward, shredding soft tissue and drawing it into the digestive tract. Each hunt was efficient, controlled, and final. Even at its size, Anomalocaris was vulnerable to change. The ecosystems it dominated were dynamic, their chemistry shifting with the planet's own cycles. Oxygen levels, temperature and nutrient flow all fluctuated, sometimes dramatically. The specialization that made it powerful also made it dependent on stability. As new competitors evolved and the environment changed, its dominance waned. Yet for millions of years it remained the undisputed master of the ocean, a symbol of what evolution could achieve when opportunity met innovation. Its fossils appear in diverse locations: Canada, China, Australia, Greenland, testament to its global success. Each specimen tells the same story. A body designed for control, an organism that embodied the Cambrian's restless experimentation made real. To hold one of those fossils today is to hold the imprint of the ocean's first apex mind, a creature that brought intent to the ancient waters. It didn't think as we do, but in its own mechanical way, it anticipated, it reacted, it learned. Every movement was a decision refined through generations. For the creatures of its time, Anomalocaris was the embodiment of inevitability. Its presence meant that life could no longer rely on chance or simplicity. To survive in its shadow required innovation, armor, speed, camouflage, or strategy. Each adaptation it provoked gave rise to new forms, and in this way, it became the architect of diversity. Its hunger shaped evolution far beyond its lifespan. Even after it disappeared, the structures it inspired continued to define life's possibilities. When paleontologists first reconstructed its form accurately, many remarked on how alien it seemed. But that strangeness is deceptive. The logic of Anomalocaris is the same logic that drives every predator that followed: detect, pursue, capture, consume. It may have looked bizarre, but its behavior would be instantly recognizable. In its flowing movements and watchful gaze, we can trace a direct line to every later hunter, from mantis shrimp to raptors to the predators of today's oceans. Its alien beauty lies not in its difference from modern life, but in its familiarity, the shared code of predation written across deep time. It's easy to imagine that the Cambrian seas were dominated by chaos, but Anomalocaris represents the first hint of order, of hierarchy. It occupied a clear position at the top, its existence defining the boundaries of survival for everything below. For the first time, there was a creature that no other could challenge. The balance of nature, primitive as it was, now had structure. Energy flowed upward through layers of prey until it reached this singular hunter, where it ended in transformation. Even in death, Anomalocaris shaped the world it left behind. Its remains settled into the seafloor sediments, becoming part of the nutrient cycle it once ruled. Over millions of years, its body turned to stone, preserving the blueprint of predation for scientists to find 500 million years later. When those first fossils were unearthed and identified, they told us something fundamental about our own origins, that the instinct to pursue and the awareness that accompanies it are among life's oldest inheritances. The reign of Anomalocaris did not last forever. Evolution, once set in motion, never stops refining. New forms rose, smaller, faster, more specialized. These same forces that had lifted it to dominance eventually pushed it aside. But for a time, its presence defined an era. It was the proof that complexity could scale, that intelligence, however primitive, could manifest in structure and behavior. The Cambrian Ocean was never the same after it appeared. The age of soft drifters had ended. The age of strategy had begun. As we look back across 500 million years, it's difficult not to feel some admiration for this strange creature. It represents a moment when life, through nothing more than incremental change, reached a level of precision and purpose that still resonates. In the flow of its body and the geometry of its eyes, we see evolution at its most confident, unafraid to combine, to stretch, to redefine. Anomalocaris was not just the apex of its own ecosystem, it was a prototype for the future. Beneath the Cambrian sun, in waters warm and clear, it glided effortlessly through the ancient sea. Below it, trilobites crawled in cautious silence. Worms retreated into burrows. Tiny swimmers scattered at the flicker of its shadow. The ocean trembled with new awareness. For the first time in Earth's history, there was something to fear. For every predator that evolution has ever imagined, there has always been a response. The emergence of Anomalocaris and the other hunters of the Cambrian did not go unchallenged. The prey learned to endure. The soft, fragile world that had once floated in near-perfect vulnerability began to harden. Shells thickened, spines erupted, bodies flattened against the seafloor. Movement became calculated, cautious. Fear, though not yet known by name or thought, found its first biological form. The age of armour had begun. Before the great predators appeared, life had little reason to defend itself beyond simplicity. The earliest multicellular organisms had flexible membranes, sometimes reinforced with organic fibres, but they lived in a realm where the greatest threat was scarcity, not pursuit. That changed once the first hunters arrived. Every encounter between prey and predator became a test of structure. Those that survived were those that had stumbled upon protection, whether through hardness, concealment, or speed. Over time, those traits accumulated, and the fabric of the ocean transformed. The Cambrian period was not a single moment of innovation, but a long contest of adaptation. Each advantage demanded an answer. The teethless, clawless mouths of early predators still exerted pressure strong enough to shatter unprotected flesh. In response, many small organisms began to incorporate minerals from the water, calcium carbonate, silica, and phosphate, into their outer layers. The result was the first true armour. These shells and plates provided rigidity, allowing their owners to resist attack, but they also introduced a new challenge: weight. The trade-off between defence and mobility became one of evolution's oldest negotiations. The evidence of this transformation is written in the fossils themselves. In rocks dating from the early Cambrian, we find microscopic fragments of armour, tiny tubes, scales, and spicules from creatures that once lived on the ocean floor. Some belong to early mollusks, others to simple worm-like animals that developed chitinous casings. These minute structures, sometimes only millimetres long, were the prototypes of exoskeletons. They represent a quiet but decisive shift in evolutionary strategy. For the first time, survival depended not only on what an animal could do, but on how it was built. Trilobites were among the most successful examples of this innovation. Their jointed, calcified shells offered both protection and flexibility, each segment interlocked with the next like a series of armoured plates, allowing them to curl into tight balls when threatened, a behaviour still mirrored by modern pillbugs, their distant descendants. When rolled up, a trilobite presented a smooth, impenetrable surface, hiding its vulnerable limbs and soft underside. This simple act of folding became one of the most enduring defensive strategies in the history of life. But armour alone was never enough. The predators evolved sharper tools, stronger limbs, and greater force. The trilobites responded in kind. Some species grew long spines across their backs and sides, turning themselves into living fortresses. Others adapted to new habitats, burrowing deeper into the sediment or venturing into darker waters where fewer predators prowled. Every generation tested a new variation, and evolution kept what worked. The variety of trilobite designs that emerged, smooth, spiny, ridged, flat, speaks to the relentless experimentation of nature under pressure. Not all defense was physical. Many creatures turned instead to evasion. Mobility became an armor of its own. The same evolutionary arms race that had refined the flapping propulsion of Anomalocaris also drove prey species to develop better means of escape. Some learned to swim faster by beating cilia or undulating flexible bodies. Others developed streamlined shapes to glide through the water with minimal resistance. The once slow and sedentary seafloor became a place of bursts and retreats, ambushes and evasions. Every movement mattered. In the fossil layers of the Burgess Shale, the diversity of these adaptations is astonishing. There we find animals like Wiwaxia, its body covered in rows of overlapping scales and long dorsal spines. It was not built for speed, but its armoured coat deterred attack. If threatened, it could anchor itself to the sediment and wait until danger passed. Nearby lived Hallucigenia, a creature so peculiar that its orientation puzzled scientists for decades. With spines jutting from its back and flexible tentacles beneath, it likely used those spikes to discourage predators while walking slowly across the seafloor. To modern eyes, these creatures look whimsical, even absurd, but in their design lies pure evolutionary logic. They were experiments in survival, shaped by the same pressures that forge all resilience. The rise of armour and evasion also changed the balance of ecosystems. Predators could no longer feed at will. They had to adapt, developing more precise appendages, more efficient digestive systems, and stronger sensory capabilities to overcome defences. In turn, prey diversified further. The result was a feedback loop that accelerated evolution across the entire Cambrian biosphere. The more that life learned to defend itself, the more inventive predation became, and with each cycle, complexity deepened. Among the new defensive forms, burrowing was one of the most effective. Animals that could move beneath the surface of the sediment found refuge from sighted predators above. The seafloor became riddled with tunnels and chambers. Some species lived their entire lives below ground, feeding on detritus and avoiding open exposure. Others emerged only briefly to graze or reproduce before retreating again. These behaviours left behind intricate trace fossils, patterns of winding burrows, feeding trails, and escape paths that still mark the rock today. They are in essence the signatures of fear, carved into the ancient mud. As the contest between attack and defence intensified, new sensory systems evolved to match. Eyes grew larger and more sensitive. Predators could now detect subtle movement or faint shadows cast by hidden prey. In response, some animals developed the opposite strategy: stillness. To freeze in place, blending perfectly with the background became a form of invisibility. Even among simple creatures with no concept of camouflage, the ability to avoid motion when threatened increased the chance of survival. From this instinct came the earliest versions of concealment, behaviours that would one day become mimicry, disguise, and deception. The interplay between armour and evasion was not a war in the human sense, but a dialogue. Each adaptation was an answer to another, each innovation a question waiting to be met. Evolution has no plan, only persistence. Yet through countless small steps it crafts equilibrium. In the Cambrian Ocean, that equilibrium was dynamic, constantly shifting but always returning to balance. Predators could never grow too efficient without driving their food source to extinction. Prey could never become completely invulnerable without sacrificing the ability to feed or reproduce. Life danced on the thin line between risk and safety, and that dance created diversity. The defensive adaptations of the Cambrian also changed how energy moved through ecosystems. Armoured bodies required more resources to grow, and so prey needed to feed more efficiently. This drove further innovation in feeding structures, rasping tongues, filtering appendages, siphoning tubes. As energy demands increased, so did the productivity of the entire system. The Cambrian seas became not just more complex, but more active. Every organism, from the smallest grazer to the largest hunter, contributed to an ever-accelerating cycle of creation and consumption. The sensory dimension of this arms race is perhaps its most fascinating aspect. As prey evolved defences, predators evolved patience. Vision, which had first arisen as a simple tool for navigation, became the foundation of strategy. To wait, to stalk, to anticipate. The behaviours we associate with intelligence began here. An anomalocaris gliding above the seafloor might slow its movement, watching for the faint stir of a trilobite's limbs beneath the silt. The trilobite, in turn, might detect the shift in current or light and freeze. For minutes, neither would move, each measuring the other's silence. These silent contests, repeated endlessly across millions of years, refined reflexes into thought. In this exchange of offence and defence, complexity flourished. The Cambrian explosion was not just about the appearance of new forms, but the relationships between them. Armour and evasion did not exist in isolation. They were the products of pressure and opportunity intertwined. The more a predator improved, the more sophisticated its prey became, and each cycle left behind traces that shaped future generations. The diversity of life today, the endless variety of shells, scales, and instincts, traces back to those first fragile defences forged under the threat of anomalocaris. Even the structure of the seafloor changed under the influence of these adaptations. As more creatures began burrowing and digging, the once stable microbial mats that had covered the ocean floor were disrupted. This created new habitats, new sources of food, and new environmental challenges. The boundaries between surface and substrate blurred. Some animals evolved transitional lifestyles, spending part of their time buried and part exposed, feeding from both worlds. Others exploited the burrows of their neighbours, turning shelter into hunting ground. The Cambrian seafloor became a complex, layered ecosystem, every inch alive with tension and motion. The concept of armour extended beyond shells and spines. Chemical defences also emerged. Some sponges and worm-like organisms developed toxic coatings or unpleasant secretions to deter predators. Though invisible to the fossil record, these adaptations likely played a major role in survival. They represent another form of evasion, not through speed or strength, but through deterrence. Life had discovered that sometimes the best defense was to make oneself undesirable. Over time, these strategies became integrated. Many creatures combined physical protection with behavioral tactics. A trilobite might rely on its shell for safety, but also burrow quickly when threatened. A worm might secrete mucus to slip away from a predator's grasp, while reinforcing its burrow with sand grains for added defense. The layering of strategies created resilience. No single adaptation guaranteed survival, but together they formed a system capable of enduring constant change. When we study these fossils today, we see not just static remains, but the memory of motion. The curvature of a spine, the shape of a shell, the pattern of a burrow, all are responses to an ancient conversation between life and danger. In those patterns lies the history of resilience itself, Every scale and segment tells a story of pressure endured and overcome. The predators, for all their dominance, could not erase that resilience. In fact, they depended on it. Without resistance, evolution stagnates. The power of Anomalocaris and its kin was meaningful only because their prey continued to adapt. The Cambrian Ocean thrived on that balance, a perpetual exchange of innovation that sustained its vitality. The more life struggled, the more it flourished. Armour and evasion are not merely tactics of survival, they're expressions of life's creativity under constraint. They mark the point where existence stopped being passive and became participatory. Every defence built against a predator was also an act of invention. The shells that gleamed beneath the Cambrian sun, the burrows that wound through ancient mud, the stillness of an animal waiting in perfect silence, all were solutions, each one unique, each one the product of necessity turned into art. The great predators would continue to evolve, growing faster and smarter, but they would never again face a world so unprepared. The age of vulnerability had ended. From this point forward, every attack would meet an answer, every hunter a challenge. The ocean had learned to defend itself, and in that endless contest between pursuit and protection, life discovered the balance that would sustain it through every age to come. Beneath the waves, the rhythm of that balance continued, a flicker of motion, a moment of stillness, the eternal pulse of adaptation shaping the world one heartbeat at a time. The seas never stopped moving. The waves above marked the passage of days, the cycles of light and dark, but below another kind of motion carried on, slower and deeper. It was not the movement of water, but of change itself. Every generation of creatures born in those Cambrian waters added something new to the pattern. Some grew harder, some swam faster, some developed strange shapes that pushed the limits of what life could become. The result was not chaos, but choreography. Each mutation, each adaptation, each response was part of a grand, unending performance, the dance of evolution. By the middle of the Cambrian period, the ocean had become an ecosystem of incredible complexity. What had once been a flat landscape of soft-bodied grazers now pulsed with energy and variety. Trilobites crawled over the sediment, eyes scanning for both food and threat. Sponges filtered water through intricate canals, recycling nutrients. Worms twisted and tunneled, stirring the seafloor into new textures. Predators like Anomalocaris glided between them, their compound eyes catching every flicker of motion. This was no longer the simple, quiet world of early life. It was a living network of reaction and counter-reaction, of cooperation and competition intertwined. Every species existed not in isolation but as part of a larger system of exchange. The evolution of one could not be understood without the others. A new shell meant a new feeding mechanism. A new eye meant a new way to hide. The dance was constant, its steps guided by invisible rhythms of survival and reproduction. Over time, this interaction created stability through diversity. The ocean found balance not by resisting change, but by embracing it. The more life diversified, the more resilient it became. This dynamic is what defines evolution at its deepest level. It is not simply a process of improvement, not a march toward perfection, but a continuous balancing act. Traits that serve one generation may become burdens in another. What thrives in abundance today may vanish tomorrow when the environment shifts. In the Cambrian, this truth was on full display. The same conditions that allowed Anomalocaris to dominate eventually gave rise to competitors that undermined its supremacy. No adaptation was permanent. Everything was temporary, flexible, alive. One of the most striking aspects of this era is how rapidly innovation seemed to unfold. Fossil evidence shows that within a span of only a few million years, the number of animal groups increased dramatically. Many of these early experiments in form, some successful, some short-lived, represent the foundational designs from which later life evolved. From soft-bodied worms came the ancestors of arthropods, annelids, and mollusks. From primitive chordates came the first hints of backbones, structures that would one day allow creatures to leave the sea entirely. The Cambrian was not just a biological event, it was a statement of possibility. Each new adaptation introduced a ripple that spread through the ecosystem. When vision became widespread, behaviour changed. When shells hardened, feeding strategies shifted. When muscles grew stronger, motion diversified. These feedback loops gave the ocean a rhythm that seemed almost deliberate. But there was no direction, no purpose. The dance was self-organising, driven by nothing more than variation, inheritance, and time. Yet from that simplicity emerged complexity beyond imagination. Imagine watching this transformation not as a human observer, but as one of the creatures within it. The water around you hums with motion. Shadows drift above, refracting light into fragmented beams. Every vibration carries meaning, a signal, a warning, a chance. The ocean is alive with information, and survival depends on interpreting it correctly. You feel the current shift as a predator passes nearby. You sense the faint disturbance of sediment from a burrowing neighbour. You move, react, adjust, live. Each response, though unconscious, contributes to the greater flow. Evolution works not through grand decisions, but through small interactions repeated endlessly, each one shaping the next. This interplay between chance and necessity is what gives evolution its elegance. Mutations occur randomly, but their survival is anything but. The environment, the web of relationships between species, and the pressures of energy and competition all filter those mutations into patterns of enduring design. In the Cambrian, the abundance of ecological niches created space for countless experiments. Some animals evolved to graze, others to filter, others to scavenge, still others to hunt. None of them knew their place in the system, yet together they constructed one of the most balanced ecosystems the planet had ever seen. The fossil beds that preserve these creatures, such as the Burgess Shale and Chengjiang formations, are like snapshots of a vast performance frozen in time. When scientists split the layers of stone and reveal the impressions of delicate bodies pressed flat for 500 million years, they are not merely studying anatomy. They are witnessing relationships. The spacing of fossils, the orientation of bodies, even the direction of sediment flow tell stories of how these creatures interacted. Some died mid-motion, caught in sediment slumps. Others were preserved in clusters, suggesting mass events or social behaviours. Each piece of shale is a single frame of evolution's film, a brief moment in an endless sequence. It's easy to describe this process as progress, but that implies intention, and evolution has none. What we call success in nature is only persistence, an unbroken chain of survival through change. The Cambrian explosion shows that the most enduring pattern of life is not dominance, but adaptation. No creature remained supreme for long. The only constant was transformation. Every advantage carried within it the seed of obsolescence. The same jaws that once crushed prey could become useless if the prey learned to burrow. The same armour that once deflected attack could become a prison when speed was needed. In this way, evolution dances not forward but in circles, each step creating and undoing itself in turn. Within this movement lies an important truth. Complexity is not an endpoint but a byproduct. The more interactions an ecosystem supports, the more intricate its participants become. In the Cambrian seas, the density of life created a fertile field for complexity to grow. Each predator, prey, and scavenger depended on the others, not through cooperation but through necessity. The ocean became a living machine that refined itself continuously. It was, in a sense, self-aware, not in mind, but in structure. Every part responded to every other, forming feedback loops that echoed through time. Some of the most intriguing evidence of this interconnectedness comes from trace fossils rather than bodies. Patterns of feeding, crawling, and burrowing show that animals adjusted their behaviours based on one another. Predators avoided areas where prey were scarce. Prey abandoned zones where predators were too abundant. Over generations, these choices reshaped the physical environment itself. Sediments became layered in distinctive ways, oxygen levels shifted, and nutrients circulated differently. The dance of evolution was not limited to biology. It extended to geology, chemistry, even the flow of water itself. Life and planet evolved together, partners in a shared rhythm. As this balance matured, the boundaries between strategies blurred. Some predators became scavengers, some scavengers became prey. The line between hunter and hunted shifted constantly. This fluidity kept the system stable. In modern terms, we might call it resilience, the ability of an ecosystem to absorb disruption and continue functioning. The Cambrian oceans, though volatile, achieved this through diversity. No single species dominated completely. Every creature was both contributor and competitor, participant and consequence. When we study evolution from a distance, it's tempting to see it as mechanical, almost mathematical. But within its mechanics lies an artistry that defies simplicity. The precise way one species' adaptation influences another's, the balance between vulnerability and resilience, the endless renewal of form, these are the rhythms of the dance. The Cambrian was perhaps the first time that rhythm became visible, not in theory but in form. Every fossil from that era is a note in a symphony written by chance and refined by time. To the creatures living then, of course, there was no awareness of the pattern. Their existence was immediate, sensory and instinctive. Yet their interactions built the foundations for everything that followed. When an early arthropod adjusted the movement of its limbs to chase prey, it refined coordination that would one day allow insects to fly. When a worm's burrowing improved sediment circulation, it laid groundwork for the complex ecosystems that would later emerge on land. Each small motion had consequences stretching far beyond its time. That is perhaps the most remarkable aspect of evolution's dance, its continuity. The same principles that shaped those ancient seas still shape us now. Variation, selection, adaptation, the steps have never changed. What began as a simple cycle of survival among primitive creatures became the process that carved the diversity of every living thing. From the smallest plankton to the largest whale, from coral reefs to rainforests, all follow the same rhythm. The Cambrian was simply where the music began to quicken. The term explosion often evokes violence, but in truth the Cambrian expansion was more like the opening of a flower. It unfolded gradually but irresistibly, each petal revealing new forms, new possibilities. With every generation, life filled another niche, exploited another energy source, tested another way to move or feed or defend. The dance was not choreographed but emergent, arising from billions of small improvisations that together formed coherence. At its heart, evolution is about balance between persistence and change. Too much stability and innovation ceases. Too much flux and systems collapse. The Cambrian oceans found a rhythm between the two. Catastrophe still came, storms, sediment slides, shifts in chemistry, but the web of life absorbed them and continued. This ability to maintain equilibrium amid constant transformation is what allowed life to endure across eons. It is the same balance that sustains the biosphere today, fragile yet enduring, adaptable yet consistent. When we trace our own origins back to this time, we are following those same steps through deep time. Every human cell carries molecular echoes of Cambrian solutions, the proteins that sense light, the calcium that forms bone, the enzymes that process energy. These are ancient inventions, perfected in that long evolutionary dance and never replaced because they work. We are not separate from that story. We are its continuation. To look at the Cambrian ocean through this lens is to see not a primitive world, but a mirror of the present, stripped of its familiarity. Every creature, every movement, every adaptation speaks to the same logic that governs life now. Survival demands creativity. Pressure generates beauty. Change is inevitable and balance is temporary. The dance continues, always improvising, never ending. And so the waters of the ancient earth shimmered with motion. Tiny swimmers darted through beams of filtered light. Armoured trilobites scuttled across the sediment. Sponges drew silent breaths through their pores. Above them, hunters glided in long arcs, each movement both threat and grace. The ocean was alive with conversation, every gesture answered by another. In that dialogue, life found its rhythm, a rhythm that has never stopped beating. Even as new forms replaced old, even as extinction swept through the seas, the pattern persisted. The dance never truly lost a step. It only changed partners. What began as the simple stirring of cells in darkness had become an intricate choreography spanning the planet. Evolution, once a whisper in the tide, now moved with confidence, shaping not just life but the world itself. And still, it danced. Through triumph and loss, through silence and storm, through every twist of adaptation and every quiet survival, it danced. The Cambrian seas, restless and radiant, were its first grand stage, a stage upon which the story of all living things began to find its rhythm, one step at a time, in the endless dance of evolution. By the time the Cambrian seas reached their full flourish, something profound had taken hold beneath the surface. Life had begun to organise itself. The chaos of countless new forms, each feeding and fighting in its own way, started to settle into a pattern, a structure that governed who ate whom, how energy flowed, and where balance could be found. It wasn't designed or directed. It arose naturally from the laws of need and consequence. Yet it had all the hallmarks of an architecture, built not of stone or logic, but of hunger, instinct, and evolution itself. These were the first food chains, the earliest frameworks of ecological order, and their architects were not the strongest or the largest, but the ones who unknowingly learned to link survival together. Every creature, from the smallest plankton to the fearsome Anomalocaris, played a part in constructing this new order. It began, as it always does, with light. The shallow seas of the Cambrian were awash with sunlight, filtered through mineral-rich water that tinted it in hues of green and gold. Within that light, tiny photosynthetic organisms converted energy into life. Algae, cyanobacteria, and simple protists bloomed across the ocean's surface, forming invisible pastures of productivity. They were the foundation of everything that followed, the silent builders of energy from which all else arose. These microscopic producers fed the first layer of consumers, small grazers, filter feeders, and detritivores that sifted particles from the water or scraped them from the sea floor. They didn't hunt, they harvested, living off the abundance that sunlight and chemistry provided. Worm-like creatures ploughed through soft sediment, stirring nutrients into motion. Sponges filtered gallons of water each day, capturing stray cells and organic debris. Small arthropods scraped microbial mats, their limbs moving in patient repetitive rhythms. Through their feeding, they broke down matter, circulated oxygen, and distributed nutrients. In doing so, they unwittingly maintained the balance of their own world. Above them moved the next tier, the predators, the opportunists, the scavengers. Anomalocaris, radiodonts, and other swimmers filled this role. They fed on those smaller creatures, keeping their numbers in check and ensuring that energy flowed upward rather than stagnating at the base. When they died, their remains sank back to the seafloor, providing food for decomposers that completed the cycle. Nothing was wasted. Every death fed another life. Every motion turned energy into form. This was the first true ecosystem, a self-sustaining network of interaction, a living system that regulated itself through the constant exchange of need and response. To understand how intricate this system had already become, consider the scale at which it operated. A single square metre of seafloor could support thousands of individuals from dozens of species. Tiny scavengers cleaned up organic waste. Filter feeders drew in microscopic plankton. Predators patrolled overhead, each adapted to exploit a particular niche. If one population grew too large, others responded, either by feeding on it or by being displaced. This natural feedback prevented collapse. Even in its earlier stages, life had discovered equilibrium not through control, but through interaction. The architects of this balance were not conscious of what they built. Evolution assembled their roles through trial and error, sculpting each species to fit into the gaps left by others. When one organism developed a new way to feed, another evolved to counter it. When one niche emptied, new forms appeared to fill it. The result was an invisible web connecting every creature to every other. For the first time, Earth hosted not just individual species but systems, entire communities functioning as cohesive units. The Cambrian seas were the birthplace of ecological order. One of the great lessons of this period is that balance does not come from stability, but from constant movement. Every link in the food chain was both vulnerable and necessary. Producers required grazers to recycle nutrients. Grazers needed predators to prevent overpopulation. Predators depended on prey to sustain their energy. The death of one sustained the life of another, and so the circle continued. This interconnectedness made the system resilient. Even when environmental shifts disrupted one layer, others adapted to fill the void. It was not perfection, but flexibility that ensured survival. In these early oceans, the role of scavengers was especially critical. When larger creatures died, their soft tissues became a feast for smaller organisms, worms, arthropods, and bacteria that consumed them completely. This recycling of organic matter returned nutrients to the system, fueling new growth. Without scavengers, the seafloor would have become choked with decay, suffocating everything around it. Instead, these quiet cleaners kept the ocean fertile. Their unseen work made them some of the most important architects of the Cambrian world. Even if their names are lost to time, the structure of the food chain also shaped behaviour. Predators that hunted efficiently thrived. Those that relied on chance dwindled. Prey that learned to hide, flee, or harden their shells lived longer, producing more offspring. Over time, these behaviours reinforced the food web's stability. The more diverse the responses, the more adaptable the system became. This dynamic balance ensured that life could persist through fluctuations in climate, chemistry, and geography. The Cambrian Ocean was not a static environment. It shifted constantly with tides, storms, and the movements of the continents. Yet through it all, the web held. If we could compress the millions of years of the Cambrian into a single day, we would see this structure form like a living city. At dawn, the first microbial mats spread across the seafloor, colonizing bare rock. By midday, the grazers arrived, carving paths through the film of life. By afternoon, the predators appeared, chasing and devouring, redistributing energy. As evening fell, the scavengers cleaned what remained, returning nutrients to the cycle. And when night came, the next generation began again, building upon what was left. Each turn of the cycle refined the pattern. Each repetition strengthened the architecture. The diversity of feeding strategies that evolved during this time is astonishing. Some organisms filtered plankton directly from the water using fine appendages. Others scraped surfaces with hardened mouthparts. Still others developed suction mechanisms to extract soft tissue from shells. Predators employed raptorial limbs, pincers, or suction mouths to capture prey. Scavengers followed chemical trails drawn to the scent of decay. Each adaptation carved out a unique role within the web. The food chain was not a simple ladder, but a complex mesh of intersecting pathways. Energy flowed through it in every direction, creating stability through redundancy. This system also introduced hierarchy, not in the sense of dominance, but in the flow of energy. The producers form the base, supporting the consumers above them. The top predators, though powerful, depended entirely on the abundance below. This relationship ensured that no level could exist without the others. In this way, Anomalocaris and its kin, despite their might, were bound to the same rules as the smallest plankton. The ocean was a democracy of necessity, each participant equal before the law of survival. The food chains of the Cambrian were the prototypes for all ecosystems that followed. The structure they established, producers, consumers, decomposers, remains unchanged after 500 million years. Every forest, reef and grassland on Earth still operates on this blueprint. The details have changed, the players have evolved, but the pattern endures. The architects of that first web wrote a code that life has never abandoned. For scientists, reconstructing these early food chains requires detective work. Fossils alone reveal little about who ate whom, but by studying the size, shape and wear patterns on fossils, researchers can infer diets. Bite marks on trilobite shells, for example, reveal the presence of predators strong enough to pierce armour. Fossilized gut contents show what these creatures consumed. The remains of smaller animals, bits of organic matter, even entire organisms swallowed whole. Trace fossils, such as burrows and feeding tracks, offer further evidence of behaviour. Combined, these clues paint a vivid picture of an ocean humming with interaction. The energy flow within these systems also influenced evolution on a global scale. Areas with high productivity, where sunlight and nutrients were abundant, became centres of diversification. There, species radiated rapidly, exploring new ecological roles. Regions with lower productivity favoured specialisation and efficiency. The distribution of resources shaped the geography of life, determining where innovation occurred and where extinction loomed. Even the earliest food webs reflected geography's influence, proving that evolution was not just biological, but environmental. One of the most important outcomes of these food chains was the development of feedback between life and environment. As organisms fed, grew, and died, they altered the chemistry of the ocean. Increased oxygen levels allowed for larger bodies and higher metabolic rates, which in turn enabled more active predators and more resilient prey. This biological engineering gradually transformed the entire planet. The architects of the food chain were also, unknowingly, the engineers of Earth's habitability. It's humbling to think that all of this, the cycles of growth, consumption, and decay that sustain every ecosystem today, originated in those primordial waters. The first grazers stirring the sediment, the first scavengers cleaning remains, the first predators striking from above. Each one contributed a piece to the structure we still live within. The food chain is not an invention of intelligence, but a natural consequence of life itself, a system that arises wherever energy and diversity coexist. In this architecture, there was no morality, no hierarchy of worth. The smallest photosynthetic cell was as vital as the grandest predator. Every link was necessary, every exchange sacred in its own silent way. The Cambrian Sea knew no kings, only participants. Its stability came from equality, from the fact that everything living was also temporary, replaceable, and dependent. Even Anomalocaris, supreme in its time, was just one node in a larger web that would continue long after it vanished. As the Cambrian drew toward its close, the food chain's architecture deepened. New species appeared to fill smaller niches. Some specialized in breaking down specific materials. Others evolved to exploit narrow environmental windows. Ecosystems became layered not just vertically, but horizontally, spreading across habitats. Coral-like reefs began to form, providing structure and shelter for diverse communities. The seafloor teemed with burrowers, the midwaters with swimmers, the shallows with grazers. The system had matured. It was no longer a simple chain, but an intricate network of connections, a living architecture that could bend without breaking. When viewed through the lens of deep time, This architecture is not static but symphonic. Each extinction event, each evolutionary burst, each migration or adaptation adds new instruments to the music. The Cambrian provided the opening movement, introducing the themes and motifs that would play out through every age to come. The architects of the food chain were the composers of that first melody, their interactions setting the tempo for the rest of life's history. The beauty of their design lies in its simplicity. Energy flows from light to life, from one body to another, endlessly recycled through death and decay. No creature hoards it. All must pass it on. The ocean, then and now, is a place where existence itself is shared. Every predator's success feeds the next generation of prey. Every fallen shell nourishes new growth. In that endless exchange, life finds meaning not in permanence, but in participation. Beneath the waves of that long-vanished world, the architects of the food chain continued their quiet work. They grazed, hunted, decomposed, and began again, unaware that they were building the foundation of all future worlds. Their design would outlast them all, surviving the rise and fall of continents, the freezing of oceans, the birth and death of species beyond counting. And though their names are lost and their shapes strange, their structure remains, the invisible architecture that still binds every living thing in the unbroken circle of life. By the time the Cambrian world found its rhythm, movement had become the language of survival. Everything that lived was shaped by motion, the gliding of predators, the slow crawl of scavengers, the drift of plankton, the subtle pulsing of sponges filtering the current. The ocean no longer simply contained life, it carried it, translated it, animated it. Every inch of the sea was in motion, from the smallest vibrating cilia to the sweeping arcs of metre-long hunters. Life had discovered that to move was to endure. Movement had always been part of biology, but in the Cambrian it became purpose. Before this period, motion was little more than reaction, a cell's twitch, a cilium's beat, a slow glide toward or away from chemical gradients. Now it had become an art, refined and diversified through evolution. The sea was a laboratory of locomotion, filled with experiments in propulsion and balance. Fins, flaps, legs, cilia, undulations, all found their place in this expanding catalogue of movement. Each new design was tested by the currents, shaped by drag, gravity, and resistance. Those that worked were copied and perfected through time. The simplest forms of motion still belonged to the smallest creatures. Microscopic plankton drifted with the tides, some adjusting their buoyancy through tiny oil droplets or gas-filled vesicles. Others beat clusters of hair-like filaments to swim short distances, steering themselves toward light or nutrients. This passive navigation may seem trivial, but it was the seed of control. To decide direction, however primitively, was to claim agency over existence. From this slow drift emerged the lineage of active swimmers, creatures that would one day conquer every depth of the ocean. The seafloor too was alive with movement. Trilobites crept across the sediment in lines, their articulated limbs working in mechanical unison. Worms burrowed through the soft mud, ploughing tunnels that aerated the ground and left behind the earliest signs of bioturbation. These movements transformed the ocean floor, mixing oxygen into deeper layers and opening new habitats for other organisms. Each step, each dig, each ripple in the silt had geological consequences. Even without awareness, these creatures were engineering their environment, building a living terrain through motion alone. Above them, swimmers like radiodonts moved through open water with an elegance unmatched for their time. Anomalocaris, with its ribbon-like flaps, demonstrated the precision that undulating locomotion could achieve. It glided rather than thrashed, conserving energy while maintaining speed. Its flaps worked like wings in water, alternating their strokes to create lift and thrust simultaneously. This form of swimming was not just efficient, It was beautiful in its symmetry. It represented a mastery of physics written into biology. From these early designs came the principles that still govern aquatic life today. To move efficiently in water requires balance between flexibility and rigidity, between propulsion and control. Evolution tested these principles in countless ways. Some creatures developed long, flexible bodies that moved like ribbons, generating thrust through waves of muscle contraction. Others evolved jointed limbs for walking, paddling, or digging. The diversity of motion mirrored the diversity of form. There was no single solution, only variations that fit the moment and the environment. The ability to move also transformed the relationships between organisms. For predators, speed meant power. For prey, agility meant survival. The chase replaced the waiting game of earlier ecosystems. Movement introduced timing, reaction, and choice. Every encounter became a dynamic event rather than a collision of chance. This change marked the birth of behavior, the beginnings of strategy, even if only at the level of reflex. To move with purpose was to predict the world a fraction of a second ahead, and that tiny glimpse of anticipation became the difference between life and death. At the same time, motion created rhythm in the ocean. Swimmers followed daily cycles, rising toward the light during the day and sinking into darkness at night. The first migrations began, not across continents, but up and down through the water column. These vertical movements redistributed nutrients, oxygen, and energy between layers of the sea. The ocean became stratified not just by temperature and depth, but by behavior. The concept of an ecosystem in motion was born, and it has never stopped since. Life's motion was not limited to muscle. The chemistry of movement evolved too. New molecular motors appeared within cells, tiny protein complexes that converted chemical energy into mechanical work. These were the same kinds of systems that drive our own muscles today. Evolution's machinery was efficient and modular, capable of scaling from microscopic to macroscopic forms without losing effectiveness. The same molecular patterns that powered the cilia of single-celled organisms powered the limbs of trilobites and the flaps of radiodonts. Motion, it seems, was so fundamental that evolution found no reason to change its foundation. The fossil record of this era tells the story not through bones, which most Cambrian creatures lacked, but through the traces they left behind. Trackways and burrows etched into ancient mudstones record paths taken hundreds of millions of years ago. Some show the gentle crawling of small animals across the seafloor, while others preserve the trails of frantic escape, sudden turns, or collisions between predator and prey. Each mark is a frozen fragment of motion, a memory of life caught in the act of living. For paleontologists, these trace fossils are among the most revealing artifacts of the Cambrian. They provide evidence of behavior, of agency, of movement shaped by need. The geometry of a track can tell how an animal walked, how fast it moved, and even how it responded to danger. In some places, entire surfaces are covered in overlapping trails, suggesting migration or feeding swarms. In others, a single deep groove winds across the rock, the final path of a creature trying to flee. These imprints turn the silent stone into a record of energy, of intent made physical. The spread of motion through the biosphere also influenced evolution's pace. Active animals reproduced faster, colonized new habitats, and encountered more genetic variation. This increased the rate of adaptation, fueling further diversification. In a sense, movement was evolution's accelerator. The more life moved, the faster it changed. This principle still holds true today. The species that migrate, explore, and interact most broadly are often the most adaptable. In the Cambrian, mobility was innovation's ally. Movement also altered perception. As animals began to swim and crawl actively, they needed ways to navigate. Vision, touch, and chemical sensing evolved to support motion, creating feedback between awareness and action. To move effectively, an animal had to sense its surroundings. To sense effectively, it had to move. The two became inseparable. This interplay between perception and motion was the foundation for later intelligence. In chasing prey or evading danger, life learned to integrate information and respond dynamically. Each flick of a fin, each twist of a limb was a form of thought without thought. The Cambrian Ocean became a tapestry of these moving lives. Schools of small arthropods darted in coordinated pulses, driven by instinctive synchronization. Worms emerged from the sand and retreated again, their bodies glinting in filtered light. Sponges swayed softly in the current, their stillness a paradoxical form of motion. Everywhere, the sea shimmered with the choreography of existence. Every movement affected another, from the faintest ripples to the gliding arc of the great predators. The physics of water dictated much of this choreography. Unlike air, water resists every motion, demanding energy for every push and pull. Yet it also supports life in a way air never could, allowing buoyancy, glide, and balance. The creatures of the Cambrian mastered its demands in ways that would echo through all future life. The undulating motion of worms became the foundation for fish swimming. The jointed limbs of trilobites evolved into the walking legs of crabs and insects. Even our own muscles, our own patterns of stride and swing, are refinements of Cambrian motion. Every gesture of movement today carries within it that ancient history. This constant motion also connected the living with the non-living. As organisms swam, crawled and burrowed, they stirred sediments and mixed layers of water, spreading nutrients and oxygen. In this way, biology became geology's partner. The living reshaped the environment, and the environment reshaped the living. The ocean's chemistry, once static, now fluctuated dynamically with the rhythm of life. Even the composition of the atmosphere above was altered, as oxygen levels rose through the cascading effects of biological motion. The entire planet began to breathe in step with the dance of its oceans. As creatures became more mobile, encounters between species increased. Contact meant conflict, but also opportunity. Some relationships grew symbiotic, tiny organisms clinging to larger ones, feeding on their waste or protecting them from parasites. Others became parasitic, feeding stealthily on hosts in motion. The web of life grew denser with every passing epoch. Motion was the thread weaving it all together, the invisible force that bound predator, prey, and environment into a single continuum. It's easy to see movement as a simple act, but in the Cambrian it became the defining principle of complexity. The ability to move independently gave organisms control over space and time. They could leave danger behind, seek new resources, and explore unfamiliar habitats. This autonomy allowed evolution to break free from the static limitations of earlier life. The first explorers were not creatures of thought but of instinct, small animals that drifted beyond their comfort zones in search of food or safety. Yet those small acts of wandering shaped the future of the planet. Exploration in its most ancient form began here. The diversity of motion also meant diversity of perspective. A burrower experienced the world as pressure and scent, navigating through darkness. A swimmer experienced it as light and current, guided by the interplay of vision and flow. A crawler lived in contact, feeling the texture of sediment through every limb. Each way of moving created a different way of perceiving, and together they expanded the sensory map of life. The world itself became richer as organisms diversified their modes of motion. Over time, new refinements appeared. Flexible exoskeletons that allowed greater articulation, muscle attachments that enabled bursts of speed, and internal fluid systems that transmitted pressure for coordinated movement. The engineering of life became increasingly sophisticated. The same mechanical principles that govern modern biomechanics were already in play. Leverage, tension, resistance, efficiency. Evolution was solving the equations of motion without knowing them, finding elegant answers through trial and consequence. This efficiency had a cost. Movement required energy, and energy required food. The demand for fuel increased metabolic rates, which in turn required more oxygen. The balance between oxygen supply and energetic demand drove further adaptation. Gill-like structures evolved to extract oxygen from water more effectively. Circulatory systems became more complex. Hearts, primitive at first, little more than muscular pumps began to appear. The act of moving had transformed physiology itself. The engine of life had been built. Even rest changed meaning in this world. To remain still was no longer the natural state but a choice, a tactic. Stillness became camouflage, a pause in the rhythm of movement that could save a life. Some creatures learned to freeze when danger approached, blending into the shifting patterns of light and shadow. Others used bursts of motion followed by complete stillness, confusing predators and conserving energy. The alternation of movement and silence, of action and rest, became another layer in the language of survival. When we think of the Cambrian seas now, we imagine alien forms gliding through ancient waters, but beneath that imagery lies something universal. The principles they lived by, the necessity of movement, the trade-off between energy and safety, the constant feedback between action and reaction, still shape every living system on Earth. Whether it's a school of fish turning in unison, a cheetah sprinting across a plain, or a human heartbeat accelerating under stress, all are variations on that same ancient theme. The world moves, and life moves with it. In the end, motion was not just a behaviour but an identity. The Cambrian Ocean was a mirror of movement, every organism reflecting a different aspect of it. The drifters embodied surrender, the swimmers control, the burrowers persistence. Together they form the dynamic equilibrium that defines all living systems. Life in motion was no longer an experiment. It was the rule, the enduring truth of a planet that learned to live by moving. Beneath those prehistoric waves, the current continued to carry the living forward. The shapes changed, the rhythms evolved, but the movement never stopped. It flowed from one age to the next, from the soft rippling of Cambrian swimmers to the beating wings and walking limbs of distant descendants. It is the one continuity that ties every form of life together, the pulse that began when the first creature dared to move against the current and never looked back. Long after the last Anomalocaris glided through its fading sea, after the soft bodies of the Cambrian creatures dissolved into silt and vanished into the turning of the world, something of them remained. The oceans retreated, the continents drifted, mountain chains rose from what was once seafloor, and yet the story of that ancient time persisted in the rocks. The Cambrian did not disappear. It sank into memory, pressed, compacted, and hidden, until time itself turned it to stone. Those stones, when split open 500 million years later, still whispered with the shapes of lives long gone. They are not simply fossils, they are echoes. Each fossil is a message written in the slow language of geology. Every fine line, every impression, every faint trace of organic film is a record of existence. Most living things leave nothing behind. The chance of preservation is so impossibly small that every fossil is an accident of perfection. A creature must die in the right place, under the right conditions, at the right moment. It must be buried quickly, protected from scavengers, sealed in low-oxygen sediment where decay slows to a halt. Then, as minerals seep into its tissues, its body becomes part of the earth itself. Over millions of years, pressure and heat transform it into stone, but the pattern remains. The ghost of movement, the memory of form. The Cambrian period, for all its vitality, is known to us only through such fragments. Most of its inhabitants were soft-bodied, and soft bodies rarely fossilise. What we know comes from extraordinary sites, rare windows where conditions preserved even the most delicate anatomy. Among these, the Burgess Shale of British Columbia and the Chengjiang Formation of China stand above all others. In their layered mudstones, creatures that would have vanished without a trace are captured in exquisite detail. Fins, gills, eyes, and even the outlines of internal organs remain, flattened but unmistakable. These fossils are not just scientific specimens, they are the impressions of a lost reality. To hold a slab of Burgess shale is to hold time itself, compressed into stillness. Within it are the forms of trilobites, arthropods, worms, sponges, and countless organisms so strange they defy easy comparison. Some look like the prototypes of familiar life, others like dreams that ended before waking. The most remarkable thing about them is their diversity. Each layer records a different moment of ecological balance, a different pulse of evolution's dance. The arrangement of fossils, their orientation and abundance, tells of currents, storms, and sudden burial events that froze entire communities in place. For scientists, these fossils are not just relics, they are data. Every detail helps reconstruct the story of how life changed. The fine striations on a fin reveal how it moved, the position of a mouthpart shows how it fed, the pattern of muscle fibers hints at strength, speed, or flexibility. By comparing hundreds of specimens, paleontologists can piece together behaviours that no eye ever saw. The Cambrian comes alive again, not as a myth but as a system, its complexity rediscovered grain by grain. Yet even as science restores these creatures to motion in our understanding, there remains something quietly human in the encounter with their remains. To look at a fossil is to face both presence and absence at once. The form is there, precise and undeniable, but the life that once filled it is gone beyond reach. It's a paradox of continuity, proof that existence leaves a mark even when all else fades. The trilobite no longer crawls, the Anomalocaris no longer hunts, but their outlines endure, carved into stone by the same forces that once shaped them from mud and water. The story of how these fossils were found is almost as fascinating as the fossils themselves. In 1909, the geologist Charles Walcott was riding through the Canadian Rockies when he noticed dark, flattened shapes on a slab of shale. Curious, he split it open and saw within the delicate impression of a soft-bodied creature, a form no one had ever seen before. Over the following years, he and his family collected thousands of specimens, uncovering a world that science did not know existed. What they found challenged every assumption about early life. Until then, the Cambrian was thought to be simple, populated mostly by worms and shells. The Burgess shale revealed complexity beyond imagination. Each new discovery expanded that revelation. The Chengjiang fossils, discovered decades later, pushed the record even further back, showing that advanced life had emerged earlier than anyone expected. Together, these sites forced a rethinking of evolution itself. The Cambrian explosion was no longer just a burst of diversity. It was a foundational moment when the architecture of modern ecosystems first took shape. The echoes in stone became the proof of life's sudden ambition. The Burgess shale and its counterparts are more than scientific archives. They are emotional ones. To stand before them is to be reminded of scale, of the depth of time, the impermanence of forms, and the persistence of pattern. These fossils are older than mountains, older than continents, older than any trace of humanity, yet they are still here. Their details so fine they can only be seen under magnification. They bridge the impossible distance between now and then, between living and extinct, between the fleeting and the eternal. When paleontologists study these fossils, they do not simply read them as specimens. They listen. Every rock layer has a tone, a rhythm. Some tell of calm waters, others of violent currents. A layer rich in certain minerals reveals the chemistry of ancient oceans. A sudden shift in composition records an environmental change or a mass burial. The sediments themselves are storytellers, their grains preserving direction, speed, and even temperature. In this sense, the rocks are not silent. They hum softly with the echoes of life's first experiments. The precision with which these fossils were preserved remains one of nature's rarest miracles. In most environments, decay begins within hours. Scavengers consume the remains, bacteria break down soft tissue, and the traces are gone. But in the few places where oxygen was scarce and sedimentation rapid, life was caught in mid-motion. A sudden slump of mud, perhaps triggered by a storm or an underwater landslide, buried entire communities instantly. Deprived of oxygen, they did not rot. Minerals replaced their tissues cell by cell, preserving detail at microscopic levels. What began as tragedy became memory. To modern eyes, many of these creatures appear alien, yet the strangeness of their forms only deepens their connection to us. Each one represents a path that evolution once explored, a possibility tested and either kept or discarded. When we look at a fossil of Opabinia with its 5 eyes and flexible trunk, we see not failure, but imagination. When we study Hallucigenia and its spines and tentacles, we see nature experimenting with solutions that would later find new expressions in other forms. Every fossil is a record of creativity, of the endless problem-solving that defines life itself. What gives these stones their emotional gravity is not just their age, but their intimacy. The fine details, the texture of a limb, the curve of a body mid-swim, are so immediate that they collapse the distance of time. They remind us that these creatures once felt the same currents, breathed the same water, and faced the same uncertainties that define existence today. The ocean that carried them still carries their descendants. The patterns they helped establish still shape the web of life. The fossils are not relics of a lost world, they are reflections of our own. As the science of paleontology advances, the fossils reveal even more. Using modern imaging techniques, researchers can now detect chemical residues of ancient pigments and tissues. They can map the distribution of trace elements to reconstruct colours, infer muscle density, even estimate how light passed through the animal's eyes. The Cambrian no longer lies in shadow, it gleams faintly with recovered light. Every new analysis adds another layer to the story, another echo made audible. The preservation of these fossils also tells us about the fragility of existence. For every specimen that endured, billions vanished without a trace. Entire species lived and died unseen, their histories erased by time. The Burgess Shale is not a full record. It is a lucky glimpse, a sliver of what once was. Yet within that narrow window lies enough evidence to reconstruct the evolution of all modern animal lineages. The thinness of the record contrasts sharply with the vastness of its meaning. It's a reminder that knowledge itself is built on scarcity, that understanding often begins with what remains rather than what was lost. Even after centuries of study, new fossils continue to emerge. Each discovery shifts the boundaries of what we know. A new species adds a piece to the puzzle, sometimes rewriting entire chapters of evolutionary history. The process never ends. The rocks continue to yield their secrets, slowly, stubbornly, as if time itself insists on being understood. And still, even with all our technology, we are humbled by how much remains unknown. The echoes in stone speak clearly, but they do not tell everything. There's a certain silence in these fossils, one that feels almost deliberate. They do not describe their world in words, they simply show it. Their forms, their arrangements, their preservation, all are enough to evoke the fullness of what once lived. When you look at a trilobite fossil and trace the ridges of its exoskeleton, you can almost imagine it moving. The grooves that mark its path in the sediment become extensions of your own gesture. The stone responds not with sound, but with presence. It holds its history patiently, waiting for touch to complete it. The continuity between these fossils and the living world is not merely metaphorical. The same minerals that formed their impressions, calcium, silica, iron, flow through us now. The oceans that buried them are still part of the planet's circulation, their salts and sediments recycled countless times. In a very real sense, The materials that remember the Cambrian are still alive in Earth's system. We walk on the remnants of those seas, breathe the oxygen they helped generate, and carry their chemical legacy within our own bodies. The past is not distant. It is embedded in every atom we share with those who came before. In studying the Cambrian fossils, we also confront the passage of time not as destruction, but as transformation. The rock layers that cradle those ancient impressions were once living sediment, then seabed, then mountain. Time does not erase, it reshapes. The same pressure that destroyed the soft bodies of those creatures also preserved their essence. The same movement of continents that buried them eventually revealed them. Even in death they participated in the planet's cycles. Life and stone are part of the same conversation. The echoes in stone remind us that the story of a life is not linear. It loops, folds, and returns. The patterns we find in the Cambrian fossils, segmentation, symmetry, locomotion, sensory adaptation, reappear in countless variations across the eons. Evolution repeats itself, refining rather than reinventing. When we recognize familiar structures in those ancient forms, we are not projecting. We are seeing continuity. The spiral shells, the jointed limbs, the bilateral bodies, they are all part of a vocabulary that began long before us and continues still. In the end, the fossils do more than record biology. They preserve moments of stillness within motion, glimpses of what life looked like before it was known. Each one is a boundary between what is gone and what endures. When we look at them, we are not merely learning about the past, we are participating in it. The act of recognition completes the circle. The echo becomes a voice again, speaking softly across 500 million years, and in that voice is everything. The rustle of ancient currents, the shimmer of light through primordial waters, the pulse of creatures that once stirred the sediment beneath an alien sun. The stone holds them all, waiting for the moment when a curious hand splits it open and lets the echo breathe once more. Even after all the movements, all the struggles, all the turning of time that the Cambrian seas began, the ocean has never truly fallen silent. It changes shape, it shifts its chemistry, it carries new species and loses old ones, but beneath every transformation, there is still the same slow heartbeat. The world that once belonged to Anomalocaris and trilobites is gone, yet its rhythm remains, carried forward by every wave and every breath that stirs beneath the surface. The quiet beneath the waves is not absence, it is the sound of continuity. If you were to dive today into any of Earth's great oceans and drift just above the seafloor, you would find yourself surrounded by the descendants of that ancient experiment. Shrimp stir the sand, worms thread their way through silt, crabs probe with delicate legs, each movement echoing the gestures of creatures that lived 500 million years ago. Fish glide where radiodonts once ruled, their fins perfecting the same principles of lift and propulsion. Every motion is familiar because it was practiced long before we appeared to notice it. The Cambrian never ended, it only changed its cast. In that sense, the ocean remembers better than we do. Its memory is physical, etched into structure and behaviour rather than words. The balance of predator and prey, the circulation of nutrients, the endless rebuilding of ecosystems, all of it began there. Every modern coral reef, every deep-sea vent community, every plankton bloom still obeys the architecture first established in those early seas. The food chains are longer now, the play is more complex, but the logic remains the same. Energy flows, life adapts, and the system renews itself. The quiet of the deep is not stillness but balance achieved through motion too vast and slow for the eye to see. There is a peculiar calm that comes with realizing how much of life's foundation was laid in that ancient world. We think of the Cambrian as distant, but its influence surrounds us constantly. The calcium in our bones once drifted in the same waters that held those first armoured shells. The oxygen we breathe was produced by descendants of the same microbes that fed early grazers. The genetic language that builds every living thing was written long before vertebrates existed. To exist today is to participate in a story that began in those shallow seas. When we study the fossils, we often imagine them as relics of something finished, but in truth, they are mid-sentence. The line of evolution that they represent has never broken. It continues through every living organism, through every act of feeding, growing, and moving. The continuity of life is the quietest miracle of all. The fact that it never truly stops. Even extinction, for all its finality, is just a rearrangement of matter and energy into new forms. Nothing is wasted. The ocean has always known this, and perhaps that is why it endures. To understand the Cambrian is to understand the origin of motion, structure, and interdependence, but also to recognize the humility of life. None of those creatures were aware of what they were shaping. They built complexity not through plan, but through persistence. Their success lay in their simplicity, in the constant exchange between survival and adaptation. Every trilobite that rolled into a ball, every worm that burrowed deeper, every predator that refined its strike, all were part of a grand improvisation that continues even now. The ocean still dances to that same rhythm, invisible but universal. If you listen closely, you can almost feel it. The pulse of waves against the shore, the steady drag of tides, the hum of unseen currents in the deep. They are reminders of the same patterns that once governed those ancient waters. The quiet beneath the waves is filled with motion, with the soft percussion of existence repeating itself endlessly. To the creatures that live there, it is not silence but life's ordinary soundscape. To us, standing on the edge of it, it feels like eternity translated into water. Modern ocean life owes more to the Cambrian than to any other age. The body plans that emerged then still define every major animal group today. Segmentation, bilateral symmetry, exoskeletons, internal skeletons, sensory organs. These were the blueprints from which evolution has built ever since. The difference between a trilobite and a crab, between a radiodont and a squid, between an early chordate and a human, is one of refinement, not reinvention. Life has always been an editor, rarely an author. The great ideas of biology were drafted early and rewritten endlessly, each version truer to the environment that demanded it. Beneath the surface, the quiet carries the memory of that editing process. The soft turbulence of water over coral, the drifting plankton clouds, the migration of fish from shallow reefs to deep channels, all are echoes of that first structured world. Every layer of the ocean tells a story of adaptation built upon adaptation. The deep sea, where sunlight never reaches, still hosts creatures whose strategies are Cambrian in spirit. Predators that sense vibrations, scavengers that recycle nutrients, filter feeders that live on the drift. The cycle persists unchanged, not because evolution has failed to innovate, but because it found what worked and never let go. If you could remove the names, the eras, and the geological labels, you would see the same relationships repeating themselves across time. One organism creates, another consumes, a third decomposes. Energy flows upward and then returns downward again. That looping exchange is the ocean's heartbeat. It is what keeps it alive even through extinction events, climate shifts, and the drift of continents. The structure is too deeply woven to unravel. The quiet beneath the waves is not emptiness, but the hum of that continuous function. The rocks that hold the fossils, the same ones that record the first shells and fins, now stand in silent mountain ranges far from the sea. Yet even they carry the memory of water. When rain falls on them and trickles into rivers, when minerals leach into the ground and return to the ocean, the cycle closes. The Cambrian still circulates through Earth's systems, through its chemistry and weather, through every tide that rises and falls. The planet remembers in its own way. We're the only ones who need to remind ourselves. There is something quietly profound in knowing that the same principles that governed those early oceans also govern us. our own motion, our own survival, our own fragility, all trace back to the same sources. The bones that let us move through air are hardened echoes of the first exoskeletons. Our eyes, built for light and colour, carry within them the design first tested by Cambrian predators. Our nerves, our reflexes, our instincts, they are refinements of ancient responses to pressure, light, and fear. Even in thought, we are extensions of that experiment. The mind, with all its complexity, is only the latest adaptation in a lineage that began with a simple movement towards something nourishing. The Cambrian seas are gone, but they never truly disappeared. Their inhabitants turned into strata, their forms pressed into shale, their chemistry folded into the crust. Yet their influence remained in every lineage that followed. The first hunters taught the world about pursuit. The first armoured creatures taught it about resistance. The first sighted beings taught it about awareness. These lessons became permanent. They are not history but anatomy, inscribed into the fabric of life itself. In quiet moments standing at the edge of the sea, you can almost feel that lineage. The sound of waves is not only the voice of the present ocean, but of every ocean that ever was. Each one built upon the last, layering memory upon memory until the sound became timeless. The air tastes of salt because it has always done so. The horizon moves with the same rhythm that once swayed the sponges and trilobites. Time changes form, but the essence persists. Scientists sometimes describe evolution as blind, but that description misses its deeper elegance. It does not see forward, but it remembers backward. Every successful adaptation carries the memory of what came before. The gills of fish remember the flaps of radiodonts. The wings of birds remember the limbs of amphibians that once swam. Even our lungs remember the chemical hunger of early cells for oxygen. Evolution is memory written into structure, and the ocean is where it first learned to remember itself. In that remembrance lies the real continuity between past and present. The quiet beneath the waves is not only geological or biological, it is emotional. It is the calm that follows understanding, the stillness that comes when complexity finds its balance. Life, for all its chaos and competition, tends toward equilibrium. The Cambrian showed that even the most violent struggle between predator and prey could create harmony at a larger scale. Each act of consumption, each adaptation, each extinction contributed to stability. That principle endures. The ocean, in its vastness, still holds that peace, not in still water but in perpetual balance. If we could watch the Cambrian seas and today's oceans side by side, we would see more continuity than difference. The shapes have changed, but the behaviour is familiar. Movement, feeding, reproduction, defence, all remain variations of the same script. The choreography of life continues without pause. The ocean never learned to stop dancing. It only changed its rhythm. Even now, every tide, every current, every heartbeat in the deep carries that rhythm forward. To understand that continuity is to see ourselves as part of it. We're not observers standing apart from evolution, but participants within it. The atoms that make our bodies have cycled through oceans, stones, and living things countless times. We belong to the same process that built trilobites and sponges. The quiet beneath the waves speaks of that belonging. It does not demand recognition. It simply exists, waiting for us to listen. If you drift far enough from shore, away from the noise of the surface world, the sound changes. The water becomes thick and steady, and every vibration slows. You begin to feel rather than hear. The deeper you go, the more the chaos above fades into rhythm. Down there, among the dim lights of plankton and the slow pulse of unseen creatures, the world feels ancient. The pressure of the water holds you as if the planet itself were remembering what it was. It is not a memory of words or faces, but of function, of life finding its balance. That is what the Cambrian gave to the world, not just diversity but stability born of interaction. The food chains, the movement, the armour, the vision, All of it was part of a system learning to sustain itself. That lesson has carried through every extinction, every transformation, every burst of innovation that followed. Life has changed its form 1,000 times, but it has never abandoned the principles the Cambrian discovered. Everything that came later, the forests, the reptiles, the mammals, the people, exists within that same structure, powered by that same exchange of energy and adaptation. The ocean beneath us is both ancestor and mirror. In the end, the Cambrian's legacy is not in its creatures or its fossils, but in the persistence of its rhythm. The quiet beneath the waves is its final and ongoing creation, a balance so vast that it can hold both motion and stillness, both life and death, both memory and renewal. Every sound, every silence, every shimmer of light underwater carries a fragment of that first living world. And so, when we listen to the sea, what we're really hearing is time remembering itself. The slow turning of tides, the drift of plankton, the pulse of unseen currents, all are echoes of the beginning. The Cambrian has not vanished. It hums quietly beneath every wave, a constant reminder that life began in motion and never truly stopped. The ocean keeps its secrets, but it shares its rhythm endlessly, gently, through every heartbeat that still belongs to it.